We wish you all a happy and interactive learning session. The magic in new beginnings is truly the most powerful of them all. A journey of 1,000 miles begins with a single step. To lead us to that first step of the new beginning, may I request Dr. K.T. Deepak, Head and Assistant Professor, Department of Electronics and Communication Engineering, IIIT Dharwad, to welcome the gathering.
Thank you, Dr. Manjusha. Yeah. Good morning, ladies and gentlemen. A very warm welcome to all for this virtual school on development of speech recognition systems for Indian languages using deep learning and open source resources. I'm glad to say that the summer school is jointly organized by IIT Dharwad, Ekstep Foundation Bangalore, and IIIT Dharwad. I would like to thank our honorable directors, Professor Kavi Mahesh and Professor P. Seshu from IIIT and IIT Dharwad for accepting our invitation and gracing this inauguration session. I would like to thank Professor S. Umesh, IIT Madras, Dr. Vivek Raghavan, Chief AI Evangelist, Ekstep Foundation, Dr. Samudra Vijaya, Adjunct Faculty, IIT Dharwad, Professor Channappa Akki, Registrar, IIIT Dharwad, Dr. Bharat B.N., Faculty Associate, Electrical Engineering Department, IIT Dharwad, and Dr. Manjusha C.B., Assistant Professor, IIIT Dharwad, for all the support and suggestions they've given us. Also, I welcome all the participants, my fellow colleagues, faculty, staff, students, and my dear friends to this virtual school. A total of 91 candidates from different IITs, IIITs, NITs, universities, engineering colleges, research organizations, and companies are participating in this virtual school. This pandemic has created havoc globally. Slowly, we are coming in terms with it. One of the early adaptations is online classes and meetings. Taking a cue from this, a thought was can we handle fairly complex hands-on workshop on this summer school in a virtual mode? I'm really hopeful and confident that the answer would be yes. Who knows? This mode of learning may be the new norm. Already, we've had few pre-sessions. A special thanks to speakers Dr. Samudra Vijaya, IIT Dharwad, Dr. Sishir Kalita, and Shruti from RM Softtech, and bunch of volunteers as research scholars, Jagabandhu, Lalaram, Ayush, Mahesh, and Amrit, BTech students, Samana, Kavana, Arun, Ankita, Jeevan, and few more from NIT Suratkal, IIT, and IIIT Dharwad for delivering these pre-sessions. Dr. Vivek Raghavan from Ekstep Foundation, Rajat, Anirudh, and Harveen from ThoughtWorks have given tremendous support for this virtual school. I'm sure there is a lot to gain for us from their experience of building automatic speech recognition for Indian languages using a large data set of more than 10,000 hours of speech. All this would have not been possible if not for Prasanna sir. He has stood rock solid as ever for making this happen. There's a saying, information is not knowledge, only source of knowledge is experience. So one need experience to gain wisdom. Come, let us experience building ASR for our own Indian languages, starting from data collection, pruning, building machine learning and deep learning models, and go on to create some applications. Once again, I welcome all the participants and stakeholders to this 10-day virtual school on automatic speech recognition, starting from today till 30th July. Thank you.
Thank you, sir, for that warm welcome and for leading us to the first step of a new beginning. Education is not preparation for life. Education is life itself. Wisdom and learning is not product of schooling, but of the lifelong attempt to acquire it. To guide us to the path of learning through the summer school, may I request Dr. Bharat B.N., Assistant Professor, Faculty Associate, Department of Electrical Engineering, IIT Dharwad, to present the opening remarks of the program.
Yeah, thank you. Good morning, everyone. On behalf of Electrical Engineering Department, I would like to invite all of you to this summer school on speech recognition for Indian languages. When I looked at the program details, I realized that there are several advantages of attending such workshop for such summer schools. First of all, the summer school is on speech recognition for Indian languages, a hands-on approach. So most of the summer schools or workshops that you attend will either focus on theory or mostly on labs. I think this has I believe, a nice mix of both theory and practice. So that way, once you finish this summer school, I strongly believe that you can contribute to the development of open source tools for Indian speech recognition systems for Indian languages. So I thank Professor Prasanna, Triple IT Dharwad, and Xtep Foundation for organizing this workshop. And it's good to see that there are around 91 participants, which is nice to have such a vibrant audience. So I also take this opportunity to introduce all of you to Electrical Engineering Department. So at IIT Dharwad. So we have around 12 faculty members working in diverse areas of research in electrical engineering, such as speech processing, AI, machine learning, communications, VLSI, nano control engineering, and power systems and power electronics. So we have several programs. We do have a master's by research, MS by research, which is a 2.5 year research intensive program, and also a PhD program in these disciplines. So I think so this I'll take this opportunity to invite all of you, or encourage most of you, many of you who would be willing to pursue research, to consider IIT Dharwad as a potential place where you can collaborate with us. Yeah, so I think with this, I'll end my speech by congratulating the organizers, and also good luck for all of you. I'm sure you will enjoy the summer school, and you learn a lot. Thank you.
Thank you, sir, for sharing your observations, encouragement, and for guiding us to the path of new learning. You can learn new things at any time in your life if you are willing to be a beginner. If you actually learn to like being a beginner, the whole world opens up to you. Develop a passion for learning. If you do, you will never cease to grow. With this, may I request Dr. SRM Prasanna, Professor and Dean R&D and Faculty Welfare, IIT Dharwad, to deliver the introductory note about the summer school.
Good morning to all. Thank you, Manjusha. Speech processing and technology development has taken a significant deviation in the last 1 decade after this deep learning approaches ventured into speech processing area. And there is a significant surge in interest in the industry sector, especially mostly the deep learning has become a data-driven direction for development of speech technologies. Vis-a-vis, when we look in academia, it was before this deep learning came into picture, it was more domain specific. But this deep learning has given a big leap in terms of developing speech technologies at scale. So in that way, the industry teams have taken driving seat to push forward the horizons of speech technology development. Of course, as Dr. Deepak mentioned, India is a multilingual society with rich linguistic diversity. We need more and more speech groups across the country to come forward and contribute towards the development of speech technologies. I'm happy to see that there are many speech groups working even at small universities. However, this significant deviation in terms of deep learning approaches for speech technology requires expertise in terms of improved software and hardware infrastructure. Software infrastructure, I mean, we need cloud computing approaches for building systems. Also, we need GPU systems for training the models, which makes the smaller universities maybe a disadvantaged place. Further, when we look into the big players in the speech technology development, like any multinational companies to name Amazon, Google, Microsoft, Facebook, and others, of course, their interest being commercially oriented companies, they will work on only few languages in India which are commercially viable. Of course, as all of us know, we have 22 scheduled languages and several hundreds of other languages in India, which needs technologies down the way. So for that, unless there are open source initiatives to help smaller groups to come in with reference to come in touch with the software and hardware infrastructure and easy ways of collecting and processing data and building systems, it will not be possible to develop speech technologies further. So in that regard, when I met Dr. Vivek Raghavan, I was quite excited to see their efforts in XStep Foundation for last 1 or 2 years about developing open source tools for speech languages of India, which when I heard that, then I thought this knowledge needs to be percolated across different universities, academic sector, as well as industry sector. So in that regard, we jointly discussed and wrote a proposal to IEEE Signal Processing Society. They came forward to support this event. Apart from that, many other sponsoring agencies showed interest in that. Of course, as Deepak mentioned, this is an hands-on session. Initially, we thought this hands-on session will be difficult and we want to experience it for the first time. We limited about for 30 participants. Even though we closed the registration, there were so many requests. It went up to, as Deepak told, it's about 90 registered participants are there. And initially, XStep team, especially team from ThoughtWorks, handled 1 or 2 sessions to give some tutorial-like thing. After that, team from IIT Dharwad and IIIT Dharwad spent several prerequisite sessions, because we see candidates from different varied background. To bring them to some level, we had almost more than a week of prerequisite session. Then with that, we are thinking that we are well placed for taking up the sessions of the regular summer school, which starts today, which will have some few invited talks on topics related to speech recognition, and also hands-on, fully hands-on sessions. And I welcome all the participants once again. I wish you all the best. And I again thank XStep Foundation and ThoughtWorks to agree to spare time to handle this summer course along with IIIT Dharwad and IIT Dharwad. I look forward for a wonderful learning for all the participants who are part of this team. Of course, we have participants starting from NIT in Arunachal Pradesh to down south in Kerala. Hope all of them will significantly benefit from this summer school. Thank you very much.
Thank you, sir, for your insights of the program, for enhancing our understanding of the summer school, and for highlighting its uniqueness. Thank you, sir. Coming together is a beginning. Keeping together is progress. Working together is success. Unity is strength. Where there is teamwork and collaboration, wonderful things can be achieved. Wouldn't it be nice to listen from Dr. Vivek Raghavan, Chief AI Evangelist Volunteer at XStep Foundation, about XStep initiatives for developing speech and language technologies? Sir, can you please take over?
Yes. Thank you all. Thank you all. I think it is very exciting that we are having this summer school, and also it is an honor for XStep Foundation to be actually involved in this school, because we are not traditionally either a academic institution or an industry. We are actually an NGO which actually focuses on education, and that to education at the primary school level. But I think a couple of years ago, Extra Foundation said that, I think we should try to understand. Extra Foundation has a tradition of being an open source kind of agency, that whatever they build open source, and they use open source. They've always been the focus has been that way. And so therefore they said that now for learning, for education and other things in Indian languages, one of the important thing was language. And so therefore, and that was where the journey of Extra Foundation started, in saying that now lots of things are happening in deep learning, in whether it is machine translation, or whether it is speech recognition, or various kind of NLU tasks and stuff like that. So we said, this is really something that if we have to get access give access to people across the country, then we need to be doing things in all our Indian languages. And that was the origin. And really, we did not think. So we said, let us just kind of see what is happening in the open source world, and try to take those and see whether we can do things to basically make it work in Indian languages. So it has been actually quite a rewarding journey in the sense that we have seen that some of these things, despite we are not having any deep background in speech processing and other things, we are traditionally not from that background, but we were able to take these various open source things and actually build things that people found to be useful. And so I think that one of the important things that we see, that when you look at especially the combination of this deep learning things and open sourcing things, I think the most important thing is that we have to build a culture within our country where many people this is actually democratized, right? That is the most important thing that we want to achieve. And there are really three important things that you need to do. One is that we need to have access to data, and there are various different ways that that people can create data, and we want to actually, that's one of the systematic things that we want to make sure, and we want to create a movement that more and more people can collect data. We have 1.3 billion people. we should be able to collect and our languages are extremely rich. We should be able to collect data. The second thing, of course, as was mentioned, was basically access to compute, right? Because compute is another very big thing which is being here, and that is something that we have to see, that how do we get as many people as possible access to this kind of ability to actually take this data and train models and build things. And of course, there are going to be certain things which are which maybe startups may do because it is or because there is some commercial benefit, but there will be other things which they may not do because of the the immediate financial these things are not there. So that the second part is going to solve that. And the third thing is that we need to obviously make it's human resource. Obviously, we have a lot of people and we have very smart people in our country, but people need to believe that this is something that can be done and there are real benefits to be had from doing it. And that is really what we want to show, that there is no magic here. And I think that there is no magic here, and that everyone can kind of start doing this, and as more people contribute, better things will come. And that is really so what has happened as a result of some of this deep learning and other things is that it is democratized potentially. If we do it in the right way, it is democratized. More people can get involved in these things and build things for their own languages, their own domains, their own things without, and so the intent is try and make these kind of recipes and these kind of things which actually allow people to make a progress in that. And that is our vision. And my vision very clearly is that, all these new language technologies, they start off in English. But I think our goal should be that we should have English equivalence in all our capabilities. All our Indian languages should have as rich a source of these tools as English. And that is, if we can achieve that vision, and this is the first very small starting step towards that, and it has to be a movement with many people involved in that movement. So we are very excited to be part of this and at least share what we know. I mean, and I think that in the end, so that people can build more and better things from it. That's the. So with that, thank you once again to giving Xstep the opportunity to be part of this workshop.
Thank you, sir. As you said, language differentiates mankind from other living beings. And it's a nicer initiative taken by EGSTEP as the focus is for developing speech and language technologies. Thank you, sir, for taking us to the journey of EGSTEP Foundation. It was nice hearing from you. You're always stronger and more resourceful than you give yourself credit for, because to be inspired is great, but to be an inspiration is an honor. To extol and to enlighten the purpose of this occasion, may I request Professor Kavi Mahesh, Honorable Director, IIIT Dharwad, to present the Director's address. Over to you, sir.
Thank you, Professor Sheshu, Professor Prasanna, Dr. Vivek Raghavan, Dr. Deepak, faculty colleagues from IIT and IIIT Dharwad, and all the participants. A very good morning to all of you. I'm very glad that we have this virtual summer school in partnership with IIT Dharwad and EGSTEP Foundation. What you have already described in terms of handling these prerequisites through tutorials and this very interesting angle, the participation, the collaboration with EGSTEP makes this an extra special summer school. I congratulate Professor Prasanna and Dr. Deepak for putting together this wonderful program. I think it's very important that we work on speech technologies and especially in Indian languages. So that's a very, very important agenda, not only from a research point of view or industry point of view, but it is also very important for our national security and national agenda as well, right? And if you look at, as Professor Prasanna rightly described it as a decade-old deviation in speech research into this machine learning and deep learning approaches, that's a very promising technology tool. I'm sure you will all learn that quickly, apply it, and there will be quick results, practical results to be achieved. My only request to all the people who are taking up research in these areas, Deepak is already smiling because he knows what I'm going to say, is also pay attention to all of the centuries of work that have been done in linguistics and the philosophy of language, right? For example, even if you take the Western literature in this, whether you look at Chomsky or the language philosophers like Wittgenstein or Austin or Saussure and so on, they all have expressed that there is some kind of universality in languages. There is some universal learning mechanism that human beings are born with, right? So Chomsky's whole model was to show that it cannot be learned only from what the mother or the parents speak to the child. So there is something innate. And that learning mechanism, if we are able to figure out and put in the machine, then we have solved the speech problem, right? So that universal. And I sincerely hope that deep learning is that technology. It will give that universality, right? But at the same time, even in our own tradition, we have that same notion of universality, right? The word, Indian word for speech is vak, right? And we treat that vak as a Devi. So Vak Devi. Vak Devi is another name for Saraswati. And our Shruti, our Vedas say, Tam Vishwarupa Pashavo Vadanti. So there is one universal language and it has Vishwarupaha, right? The worldwide variety of forms. And it says the human beings as well as animals, Pashavaha, they speak this. So that in that sense, we also have had this notion of universality, and that universal in language learning and speech processing, if we are able to crack through these technologies, that would be wonderful for us. At the same time, I think when you take up speech processing of Indian languages have certain different characteristics, especially, for example, if you take something like text to speech, I believe it is fundamentally more solvable for Indian languages than for European languages like English, right? So, if you are making sambar, you can generally throw in any vegetable into it. But if I have only Karela and I boil Karela and make sambar, the result will be rather bitter. I'm not saying that Indian languages are bitter like Karela, but just remember that maybe a different approach may work better, some kind of a hybrid approach. So if you keep this in mind, we can probably achieve a better breakthrough than what has been possible so far. Otherwise, this machine learning and deep learning is like a pot of sambar into which I throw any vegetable and I get sambar out of it. So let us not simplify it to that extent. Keep in mind the linguistics, the philosophy, and our own tradition in Indian languages, and hopefully we can achieve greater results. I wish this workshop all the best, this summer school. And if at any point, if there is anything that we can do from IIIT Dharwad to make your experience better, to facilitate this in any better way, please do let us know. Once again, a very good morning to all of you, and thank you.
Thank you.
Thank you, sir, for bringing to the limelight the core objectives and distinctiveness of the summer school. Indeed, there is universality in language. And thank you, sir, for marking the richness of linguistics philosophy by referring to Chomsky's model and for quoting Sazori. We learn myriads of new things every time we listen to you. Thank you, sir, again for that mammoth record. You are braver than you believe, and stronger than you seem, and smarter than you think. To edify and to educate better about this program, may I request Professor P. Seshu, Honorable Director, IIT Dharwad, to deliver the Director's address. Over to you, sir.
Hi, good morning to you all. Warm welcome from IIT Dharwad side. I am really happy to see that two institutes of national importance located almost across the road in Dharwad have come together. And not just that, they have joined hands with an NGO or a foundation, Step. That is the order of things in my mind. We should all work together because the problem at hand is so huge that no single person can make an impactful research at the ground level. So it is extremely heartening for me to see that you three organizations have come together. Obviously, for most of you know that I don't work in this field. I have only a bystander's view of the field over the past few decades. But it has been an exciting journey. When we were students, NLP used to be the cool thing to be doing and so on. And also the speech processing. I have seen how, as a student, I used to always get confused that speech processing should be same as signal processing. Then later on, I came to know the intricacies of these fields. But as a subject, it has grown a lot. For variety of reasons, applications are vast. When it comes to specifically this summer school applications to Indian languages, I see tremendous potential when we look at the Indian languages, because there are multiple things that we observe when we look at the way in which the internet has grown in the country, the digitalization of the whole society, economy has happened over the past few years. So if you see this, it is important that we are able to reach to all the population. We should never have this digital divide separating anyone, from getting the benefits of this technology. For that, it is not necessary that somebody should learn, a certain coding language or a particular way of working with computers and so on. So one of the features of speech processing I see is to be able to take the latest technology benefits to the doorstep of anyone who is not conversant with these technologies. That should be the goal for all of us as engineers, and to take the technology. Of course, there are people who will develop the technologies, who are deep into research, who will advance the frontiers of efficient algorithms and develop newer algorithms, newer techniques. But there are also a good number of people that should focus on taking these technology applications to the people at the grassroots level. That is when we will be able to transform the society. That, I believe, is the true import of any engineer or scientist ultimately, because we all live off the society that feeds us, and ultimately it should, whatever research technology development we do should flow it back to the benefit of the society. It is heartening also for me to know that you have had a pre-summer school workshop or tutorials. I have seen many workshops. I have myself organized workshops, but this is the first time I am really seeing that the organizers, Professor Prasanna, Deepak, and their teams from the institutions have taken trouble to find out the background of the participants and conducted a pre-workshop tutorial to build a better foundation for all of you. And I'm sure that would be very useful as you go through the deliberations of the workshop. So it shows how much they care for the participants of the workshop and make sure that the workshop delivers what it promises for everyone, irrespective of your backgrounds. So that is really nice. I am also happy to share with you, as Professor Prasanna mentioned, the importance of computing access. We have installed a very powerful CPU-based high-performance computing system, another high-performance computing system based on GPUs. We are in the process of augmenting the same. So this is available for almost every one of you to use. I'm sure Professor Prasanna would explain in due course of the workshop. For those of you who are interested, could always get in touch with Professor Prasanna and team and take advantage of this so that you are able to use this for your research. I am glad Dr. Vivek mentioned about their primary focus being on schools. So being in the North Karnataka region, sir, I can assure you that both IIT Dharwad, and I am speaking on behalf of Kavi, I hope he agrees, IIT Dharwad faculty and researcher students would be very happy to work with your foundation to improve the quality of education, contribute towards that in the schools in this region, be it computer related education or otherwise also. That would be very important for all of our students and faculty also as an activity to be engaged in, and that would be our contribution to the community around us. I used to have a dream that one day I would write a book and that would automatically be translated into multiple Indian languages and simultaneously be published. So hopefully through all this research that happens in NLP and speech processing and so on, that dream would be realized soon. The point that comes to my mind is also related to the scale and the diversity of the Indian languages. Professor Kavi Mahesh mentioned about the universality of the languages. But if you look at the participants from, as Prasanna mentioned, from Arunachal Pradesh to Kerala, so you would see that we have a plethora of languages. In fact, actually, many languages have died over the past several decades and a century. It is important to preserve these languages also, in a sense, but also to look at the scale and diversity of applications that are possible, be it from the farmers to anyone, I mean, in various regional languages, to look at the scope of applications. So I see tremendous possibilities, exciting possibilities. Wish I were probably 30, 40 years younger to take up this type of activities. I also thank IEEE on behalf of IIT and organizers, IEEE Foundation, to agree to be sponsoring this workshop and summer school. See that the participants are there from a variety of institutions all over the country. It's extremely nice to see. It's very relevant for a workshop or a summer school on Indian languages. So I am really happy that this topic has touched the nerves of all of you and you have immediately registered for this workshop. And I am glad to see that it's almost 100% attendance. It's amazing. I have never had it in my own classes. Forget workshops and It's amazing to see nearly 100% attendance. So again, kudos to the organizers as well as all the participants. As a team, I am sure you will do a lot over the next couple of weeks and later on also. But I will end with my speech with just one comment, which could be thought-provoking for all of you. With all your speech-related work, there is also a lot to learn from the silence in between. You may be thinking that perhaps I learned it the hard way over 30 years of my marriage, but no, I actually learned it as a student when I watched a Malayalam movie. I think it was in IIT Madras. The hero of the film, I don't remember the details, but he goes on tuck, 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 dialogue for about 5-10 minutes. Obviously, we didn't understand what it was about watching a Malayalam movie. Then the heroine just quietly looks at him, and all that is to be communicated is communicated in her stare. Then I realized as a student that all that this fellow has spoken for 15 minutes or so dialogue, 10-15 minutes, is all countered by just that one moment of silent pause. So there is a lot to be learned from silence also. So maybe some of you would look at that aspect also. I wish the summer school all the very best. Such a happy occasion that you are using the online medium to conduct this type of a workshop. I really hope all of you will be here in person one day very soon and interact with our organizers, look at our facilities, spend some time with IIT and IIIT and XTEP Foundation, and take the benefits of directly interacting with the people. Okay, all the best to all the participants and the organizing team. Thank you.
So for sure, we will work together and such collaboration will continue to spread the fragrance of education. Thank you, sir, for your explicit note on the potentiality and the unique intricacies of the summer school. Striving to reach out to the people at grassroots level will be achieved down the lane. Your dream of writing the book and it being translated will happen soon with the development of technology. And thank you, sir, for your wishes. And as you said in your anecdote, silence is powerful. Thank you, sir, once again. Gratitude is a powerful catalyst for happiness. It is the spark that lights a fire of joy in your soul. To express gratitude, may I request Professor Annappa D. Akki, respected Registrar, IIIT Dharwad, to propose the vote of thanks.
Am I audible?
Yes, sir.
Yes,
Okay,
sir, you
thank
are.
you. Honorable Directors of I2T and I3T Dharwad, Dr. Vivek Raghavan, Chief AI Evangelist, XTEP Foundation, Professor Mahadev Prasanna, Dean R&D and Faculty Welfare, I2T Dharwad, sponsors, keynote speakers, Dr. Bharat I2T Dharwad, Dr. Deepak I3T Dharwad, participants from various institutes and industries, teachers, learners, and others. My greetings to one and all. At the very outset, let me express my happiness to be part of such joint academic venture to spread and shower the knowledge. We are happy to see both the directors present during this inaugural event. On behalf of the organizers, let me take this opportunity to convey our sense of gratitude to the Honorable Directors, Professor P. Sheshu and Professor Kavi Mahesh, for sparing their time with us during this online inaugural event of the program. It's our pleasure indeed to extend our vote of thanks to all the four sponsors, IEEE SPS, ISCA, Tihan IIT Hyderabad, Arms of Tech Private Limited, Chennai, and the two supporters, IIT Alumni Center, Bangalore, and International Speech Communication Association. We also wish to express our gratitude to all the learned researchers, resource persons, and organizing team. It gives me immense pleasure to thank all the participants for having chosen this workshop to expand their knowledge in speech recognition. A word of appreciation to all those volunteers who have contributed either directly or indirectly. Finally, I am pleased to convey my pranams too for giving me this opportunity. Wishing the remaining days of the workshop to be filled with happy and useful learning experiences. Let me conclude. Thank you.
Thank you.
Gratitude can never be expressed through words. Yet, recording the sense of gratitude is what makes the show continue. Thank you, sir, for thanking all those who are associated with the summer school. Thank you, sir, once again. Those people who develop the ability to continuously acquire new and better forms of knowledge that they can apply to their work and to their lives will be the movers and shakers in our society for the indefinite future. Always remember, inquisitive mind invest. To add to the treasure chest of IIIT Dharwad, may I request all of you to please turn on the camera and pose for a screenshot as everything is happening virtually. Over to you, Dr. Deepak.
Thank you, ma'am. Thank you. So if all can turn on the cameras, we can have a snapshot. Thank you. Thank you. There's no click sound virtually, so snap has been taken up.
Nobody said cheese. It was silence.
Yeah, I mean, literally followed Professor Sheshu's recommendation. Yeah.
But silence processing is a very important. Silence recognition.
Yes, sir. Yes, sir. Prasanna, sir, so you can take over and let's have the session begin. Thank you, sir.
Thank you all.
Thank you all of you. Thank you all of you. This is Manjusha signing off with a hope to meet you all on such nearing occasion. Happy day and have a very good morning. Thank you.
Thank you, Dr.
Thank you, ma'am. Thank you.
Bye, sir.
Now,
Bye.
we have the first expert, Professor Umesh from IIT Madras, to enlighten us about this exciting field of automatic speech recognition. All of us know about Umesh sir. He was a faculty member at IIT Kanpur for a long time, who has established a speech research group there. Then he moved to IIT Madras, and with my association with sir goes long back, starting from 2002 onwards. Especially, he is one person who really convinced and led the teams for building practical systems in the speech recognition system for Indian languages. He brought consortium mode projects in speech recognition area from Ministry of Electronics and Information Technology, and trained research scholars across different institutes in the country, and made us to build systems and get confidence on building systems. Of course, the recent attempt by SARS group is they are driving open source challenges for all the groups in the speech recognition area, where any group can use their resources, build systems, and they will evaluate and make the results available. And also a lot of resources they are creating and making it available for people from both industry and academia to use and develop speech technologies. So then we thought this will be a very nice thing to start this summer school by listening to his experience and his kind words about what is the way forward for building speech recognition systems for Indian languages. With these few words, I welcome Umesh sir. Sir, stage is over to you, sir. Thank you.
Thank you, Prasanna. As usual, Prasanna is always glowing in whatever he says. I don't deserve all of that. So let me first, make sure the slides are proper, and then we'll start. So can all of you see the slides?
Yes, sir. Yes, we can see, sir.
Okay. So first of all, I'd like to thank Prasanna. I mean the whole IIT Dharwad group, Triple IT Dharwad, Step, for giving me this opportunity. I think it's a wonderful effort from their side, and I think it's a very important effort because ultimately we need to actually build good systems, right, in Indian languages. And for that, initially we need a lot of hand holding, and I think this workshop will definitely help you achieve almost what it targets, which is having a large group of people trying to build systems and using the appropriate resources, right? And it's a confidence building measure. It's going to be, I hope, the first of the many workshops that should come. As Professor Prasanna mentioned, we have been trying to do things where we want to introduce or involve the entire community, right, which especially involves youngsters, right? So as we get older, I think many of us are still are the new fresh blood, new ideas. Those kind of things are very important, and speech especially is very important in India. I think we can even bypass the text part of it, because just like we bypassed the mobile the landline kind of thing, wired connections, and went to wireless, I think a lot of things can be achieved just by speech, right? And it makes a lot more sense in India with so many languages. People can obviously speak, right? Reading, writing, typing skills, these are some acquired skills, but speech is something that's much more natural, right? So if I can get things done by speaking, it will make a big difference, right? And I think that's what Professor Seshu was pointing out, and many of the the Triple IT director was mentioning. So we hope this is one of the many steps. We did try, and we have been trying. So we try to involve a lot of institutes as a part of the construction project from, I think, 2010 to 2016. We did have a lot of workshops in summer, something similar to this. Of course, we had more fun because it was offline, so all of you came, right? And I remember the afternoon tea session was a big hit, because people would get together and we would make sure that we got good snacks, all of that which you're going to miss in this workshop, I'm sure. But more importantly, there was one person constant in all of this, and that's Dr. Samudra Vijaya. He is one person who has been, in speech from the beginning. Just historically, to give you an idea, Professor PVS Rao, Professor Yagna Narayana, and the whole Aligarh Muslim University, and Professor Kuldeep Paliwal. These were the initial path, pioneers who created the path for many of us to follow, right? And then Dr. Samudra Vijay is one person who is always there. We used to meet. We used to have sessions even from 9 to 12 in the night, right? Starting from morning 9, it used to go. And you would be seeing him always there, smiling and always willing to help, right? And talking to you. So I know Dr. Samudra Vijay is here. He's one person who has wealth of knowledge, right? And you should exploit that knowledge. Professor Prasanna, Professor Deepak, Step, they are wonderful people who are there to help you out, right? And then, we hope many of you take up this task. As Professor Seshu mentioned, research is a lab, right? I mean, you can get good algorithms, but ultimately, what benefits society is when it works in the real world, right? So we need things that are right at the ground level, and that is where I think India needs this idea of productization, right? So from lab prototypes to working, systems, there is a lot of engineering involved, and at all aspects, whether it's the research part or the engineering part or the implementation part, all of these are important, components in any ecosystem, right? So some of you might be interested in the fundamentals, some of you might be interested in theory, the math, some of you might be interested in making things work, right? It is a system, right? So it's going to have a lot more, in the speech part is only going to be 20-25% of any working system, right? So there are other components that have the interface, the user interface, right? Is it nice, right? So these are things that I think needs a lot of attention, right? And we hope as a community, we all collaborate, cooperate, share, right? and progress. And I hope and I wish that success for this particular workshop, and many more to come in the next few years. Okay, so having given a Gyan as an old person, let me go into the details. I'm going to give you an overview of what has happened in the last few years. Very exciting things, right? As usual, this is not, it's I'm standing on many people's shoulder, like as I said, stalwarts like Yagna and PVS Rao and Kuldeep Paliwal, and the newer generation, including Prasanna, Rohit Sinha, Deepak, you name. There are many people, and then the newer generation, right? So you have Professor Preeti Jyoti, Sriram Ganapati, Prashanta Ghosh, amazing people who have come back to India, and we hope that as a community we move forward. Okay, so, and for me personally, it is I'm an individual working in a lab, right? So obviously the contributions from my students and project staff are very important. So what I am speaking about is the effort of a group of the lab. So what I speak for is on behalf of the entire lab. So you see some photos here. These are the present members of the lab, but as I said, it's all built on history, right? So 25 30 years, more than 30, I think many of you were not born when I started teaching. So there is almost 100 200 people who have gone through the system, and we are riding on their shoulders, right? And as Professor Sheshu pointed out, it is an important part, and the union government has recognized it, right? And so we have announced in the recent union budget that what's called a national mission, right, to lower this language barrier, right? So whether I'm in Bengal wanting to speak in Tamil, or when I'm in Karnataka wanting to speak Gujarati, I should be able to speak, right? And forget Dharwad Kannada versus Bangalore Kannada versus Tamil. I am from Bangalore, so it's all very different, right? So dialects are so different, right? How do you communicate with each other? So, and whether we can lower the language barrier, which includes both the speech parts and the machine translation aspects of it. And to do that is not that we only develop algorithms, or we build some great thing for one particular application or one particular domain. What is required is to build an ecosystem, and that involves not only researchers, obviously students, and are an important component of it, but also startups. Many of you, I'm sure, have entrepreneurial kind of kick in you. You want to do it, and I think this is a great opportunity to do, right? China has done that in the last 10 years, right? So it's not a very big, if you look at Xiaomi, right, for example, I mean, that mobile, or OnePlus, right, it's hardly a 7-year-old company, 6-year-old company. So if you're willing to invest 4 or 5 years, you could make world-class products, and we could be selling it to the rest of the world, right? Especially because we are a multilingual society, right? So many of the problems that we face, right, are similar to what Europe faces, or Africa faces, or many other countries, right? So things that we develop here will resonate with many more people, right? And I like to think of this as an industry, right? We are very in its infant stages, right? Like the IT industry came up, or the transportation industry came up. What Google or Amazon Alexa or Cortana provide are some basic services, right? So it's like my analogy would be that they provide some bus service, right? So you have to pay to get onto this bus, and it's not a cheap deal, right? But buses are not the only things. Routes that they determine are not the only things. I might require routes in different directions, right? Which means in our case could be different languages. I might not. Why do I need a bus to do everything, right? I might be happy with a scooter, or or autos, or trucks, right? So we have to build, and these loosely analogous would be different domains, different applications, right? Broad, compute intensive guys versus edge. I want compute that happens very in a small footprint. So all of this is there, and we need to focus on all of this, right? So there's a big potential, I feel, for this industry, the language technology industry, as I would like to think of it, right? And there are many aspects to this language technology. I specifically speaking on
Ramesh Bukia, yeah, please. Yeah. Okay, sir, please carry on.
Yeah. If you talk about speech, as I said, machine translation is another important cog in this language technology field. You have speech to text, and then text to speech, and speaker authentication. There are many other diarization. All of these get into these pictures. So language ID, right? Many of these will be touched, right? But these are the broad three areas that are there in speech. And I'm now going to talk specifically, because I don't have much time. I give you some gyan, specifically about speech recognition in this tutorial, right? And I want to just touch at a very superficial level at what's been happening over the last 10 years, with the idea that when you spend the next 2 weeks working on these things, you see a relation to what I told you today. And of course, you need to spend a lot more time learning the depth of it, but it's going to be an iterative process. First, you have to get the big picture, and then you start looking at the details, right? So if you look at automatic speech recognition or speech to text, the task is basically taking a speech signal, right? And you have a speech signal, and the idea is to get the words that correspond to that speech signal. That is a task, right? And then, of course, whether I can make sense of the text and do something useful is where the NLP part is going to come, right? So NLP is mostly text processing. Speech to text, that is automatic speech recognition, is one task. And then once I do the conversion or find out useful information, the machine has to speak back to the user, right? And that's where the text to speech part of it comes. Okay. So I'll just give you an example. I have to mute every time others there's an echo, but I'll play 2-3 audios, and you'll see corresponding text, and then I'll come to the topic, because I have to mute a little bit.
Este es un lápiz. Este es un lápiz. Este es un perro. Este es un perro.
What did you guys listen? Can some of you say? It was always este es un and este es un, right? And now if I play the third one, there'll be an echo, but I don't know.
Este es un perro. Este es un libro.
Can you guess what this will be? So the point I want to say is, you can give the chat box, but it's always started with este es un, right? And if I don't know, and I don't know Spanish, most of you don't know Spanish, right? But you start seeing a pattern that this is a dog, this is a pencil, and so you are able to guess it should be something like this is something, right? And this is essentially how speech recognition works, right? So este soon seems to be common, and that means this is, right? So you're doing pattern recognition. You're seeing similar sounds occurring, and what we call is this, the text part is called the transcription. And so essentially we are listening, and we see a common pattern, and that we see is always related to these words, this is, right? And so I have learned, within the first few minutes, that at least I know este soon means this is, right? And somewhat similar is how we are going to do speech recognition. We are going to provide a lot of speech signals and the corresponding text, which is called transcription. Okay, but it's not easy. The point I'm trying to say is, suppose you land up in China, right? You are there for, let's say, a month. Okay, you don't know Chinese, right? Let's assume you don't know Chinese. And then you spend some time there, but nobody is guiding you, right? So you're only listening to people and learning something, right? Then you start seeing patterns. But being a human being, you can discount a lot of these things. For example, you can discount a horn, right? Or somebody sneezing or somebody coughing, because you have acquired that knowledge, even though you don't speak Chinese, that these are non-speech sounds. Okay, but for a machine, this is not obvious, that it sees a sneeze, it sees a cough, it wants to know, is that a word that I should recognize? So over period you acquire this knowledge. So even machines take time, right? We have been acquiring this information for the last 20-25, however old we are, right? We start learning right from childhood. The point is, when I land up in China, it is difficult for a human who has a super brain, right? I mean, it's really powerful, right? But to expect a machine to do something like a human is, as of now, very unrealistic. Okay, we do get certain good performances, okay, but that doesn't mean we can replace humans. Okay, the point I'm trying to make is that when you look at outputs of the ASR, the speech text, because you know the language, sometimes you're annoyed. What stupid mistake is it making? How can it be like that, right? And it is because it's similar to what you have learned when you went to China. Sometimes you cannot even pronounce the words correctly, right? And you make sounds that sound similar to it, but it's not exact. And in fact, because you make these pronunciation mistakes, what could be a compliment can as well be a derogatory word, right? So we know that, right? So if you don't know a language, you can't often pronounce properly, right? For example, a North Indian will find a lot of things difficult to pronounce from South Indian languages, even though he has learned or been in, let's say, Chennai or something, right? Or if, for example, zero versus zero, because we don't have, I mean, we learn to speak in a certain way, right? So we enunciate by listening, and some of these things, zero versus zero, or simply versus zimbly, right? That is all acquired. For me to say per is very, very difficult. For a Chinese to say r is very, very difficult. So he can only say Nalayan. He will never say Narayan, right? For him, ra sounds similar to la. Perceptually, he has been trained like that. Okay, so speech recognition is a difficult task even for humans. So be realistic about what machines can do. But we can do a lot of wonderful things. 24/7, I can have machines attending to calls, right? Human, especially in India, you see they'll keep it off the cradle, right? So there are many useful things we can do, but don't expect that we are going to change, we are going to replace humans just because we can do great speech recognition technology. Okay, that's not going to happen. Okay, so as I said, one of the important things in speech is to have proper transcription, right? And that's the way you train machines. We will see another a parallel kind of thing, which is called self-supervised learning, which has its own deficiencies, but we'll come to it. Okay, and this is true for almost all the big multinationals as of now, right? They use supervised learning, right? For example, for Google to support Indian English, right? I'm not talking about just English. They had a very good American English system. For Google to say that officially they can support Indian English, they collected more than 70,000 hours, right? They sent about 1,000 people on the ground, right? Field guys, and each guy collected from thousands of speech utterances. So Google has their systems are built on 150,000, 200,000 hours of speech data, right? Cortana, Alexa similarly sits on a huge amount of data. Cortana sits on a huge amount of data, but they're not going to share with you because this is client data for one. So all the time they're acquiring data from you. When you sign on Gmail, Google, everything, you're signing saying that they can use your data any which way that they want. Only thing they can't do is they can't share it with others, right? So that's a privacy issue that comes in, but they can do and build amazing systems, but they're not going to share it with the rest of the world, right? And that's the reason why we are trying to from our side give as much data, put as much data in the public domain, so that people have some data to work with, which is one of the first things, right? And then once you're getting familiar with the technology, you can do wonderful things, right? So once you know how to build one, it's going to be easier for the next time and the third time and fourth time, right? And the same thing is true for the industry itself. If one or two startups do wonderful things, right, then you'll see many more people interested in startups, right? So when you started e-commerce, which is an easier thing, it's not as deep a technology as speech or language or any of them. When few of them, Flipkarts and few of these delivery systems became popular, you had other people mimicking, right? So we hope that we do get many more startups in speech, right? And we also hope that we'll keep releasing data, but data is only one part. You should know how to use the data, right, efficiently, and whether we can do some interesting things with the data, right? So I will give the demo a little later, right? So I'll talk about the basics of speech, and for you to understand, right? So this is going to be slightly technical, but I've kept it very, very very superficial, so that you get a basic idea of what happens. So if you look at speech, this is a speech waveform, right? And if I took a look at two cuts of this waveform at 2 points, you see the cut here looks like this, and the cut here looks something like this. You can see that this is slowly varying, right? And this is rapidly varying. And from frequency, you know that this is a slowly varying component, so it has low frequency. And this is a rapidly varying part, so it has high frequency component. So essentially, it's a time varying signal where the frequency content changes with time, right? And when I speak, I am going to have a combination of slow, fast, everything. I mean, in terms of frequency, right? So the frequency content is changing, okay? And fortunately, speech recognition is very, very similar to handwriting recognition. So if I'm looking at a written text, right? So the speech is spoken text, spoken language. Written language is made up of alphabets or the characters, right? So if I look at English, how many characters or alphabets are there to form a word? There are 26 alphabets, right? The A to Z, right? And then if I'm trying to represent written language, I need additionally the punctuation like full stop, exclamation, comma, and so on, right? So about 32 characters is all that I need to do the written language, right? Fortunately, in speech, the spoken words, right, is not made up of, there are some basic units. Every spoken word is made up of only about 40-50 units, okay? And these units are like your alphabets. So the spoken language is made up of these basic units, which are called phonemes, right? So just like when I'm doing handwriting recognition, if I recognize the alphabets, right? From the alphabets, if I see G-O-O-D, I know it's good, right? So the word good is found by, if I can recognize the alphabets G-O-O-D in the written part. Similar in the spoken part, if I can recognize the phonemes, then I can get to the word that's underlying there, okay? And that's done usually through what's called a dictionary or a lexicon, okay? So the good part is speech recognition or spoken language consists of only some few discrete units, 40 to 50 discrete units, which are concatenated to form words, spoken words, right? For example, the sound ah, right, is formed in a particular way. So this is, you're using your mouth to produce these different sounds. You can see that ah will have a specific configuration where your tongue is, where this is closed, right? So when I say ah, right, and when I say e, you can see when I say e, your tongue is moving to the top of the palate, right? And then it's basically just behind the teeth, and you can produce e. If you see e and look at where your tongue is, it's very different from where your tongue is when ah is produced, or when oo is produced, right? So oo is basically where you can see this lip rounding and things like that that's happening, right? And what happens is, because these configurations change, these are like tubes, and tubes have resonant frequencies. Because these configurations change, each of these sounds have some dominant frequencies, okay? So if you look at ah, like in father, right, it has a dominant frequency around 750 hertz, and around something like 1250 hertz, and something around 2500 hertz. So these are the three dominant frequencies for the sound ah. And so for the sound e, you have something around 250 hertz, then around 2500 hertz, and around 3500 hertz. And for oo, it's around 250, 750, and something around 2500. Okay, so what does it mean? It means that for spoken language, I have to recognize these basic units, which we are going to call as phonemes, right? If I recognize these phonemes, I can concatenate these phonemes and form words, right? And then we'll see later, words have to be in a certain sequence, which is determined by the grammar or the language model. But my spoken recognition problem is now simplified. I have to recognize only this 40 or 50 different sounds. And given that I know that the frequencies are different, right? Somebody can you tell me on the chat box, what is the easiest way to do these phoneme recognition? What would I do? Can you write or type on the chat box? I would look out for what's called the dominant frequencies. So if I can recognize the dominant frequencies, or what's called the formants in our language, right? I can pretty much recognize the sounds, right? The basic sounds. So there are only 40 to 50, the phonemes that I'm talking about, right? And from that, I can recognize the sounds. From sounds, I can use something called a dictionary to get words. From words, I can get sentences, okay? That's the basic broad overview. And what we have historically found is that to recognize these, instead of just getting the spectrum like this, we are going to do some processing, but essentially capture that this spectral shape through something called Mel filter bank or MFCC. So this is something that you'll hear a lot. So you might hear about Mel filter bank and MFCC. These are essentially frequency content of the signal, right? That's what we are trying to capture. From the frequency content, I can find unique sounds, okay? And I have to do this because remember, speech is evolving, right? I'm saying so many different. So I'm going to say, ha, aapne kya kiya? So there's ha, ne, right? So many things are happening. Each one of those are your individual phonemes. I should mention that Indian languages are highly phonemic, okay? So pretty much what you say is what you write. So when I say k, I write k, right? But in English, for example, when I write put versus but, right? It's put versus but, right? So there is a difference, and which is not so. The Indian languages are much more phonemic in the sense that what you write is pretty much what you say, okay? And that's an advantage for Indian languages. So the Indian languages that you have, like you look at the Devanagari, right? You start with those are the proper phonemes that are there, okay? So you can see the way and are said, the tongue moves in different positions, right? And that's why most Tamil guys cannot say, and I can't say that also. Like for example, Kawa and khadag, right? The aspirated, the back part, Bengal, I mean, the Hindi guys can speak very easily. For Tamil guys, that doesn't exist, right? So we don't have that sound at all, right? So it's difficult for us, but essentially these are all the phonemes that we're talking about, okay? So what I'm going to do is, as I said, I'm going to be looking at speech as a varying time waveform, and I'm trying to find out how the frequency is changing. Each such region, I try to find out what phoneme was there, right? And that I basically am going to do by capturing these block processing or window processing based processing. So I'm going to take 25 millisecond windows and capture these basically spectral information through Mel filter bank or some other useful features, right? So these are the features that I'm going to capture every 10 milliseconds, right? And now I'm going to do a pattern classification problem. Remember, what is the idea of speech recognition? To identify the phonemes. And so given this speech vector, which captures a part of the speech signal, what was the corresponding sound, right? What is the alphabet of the spoken language? Was it A? Was it E? Was it U? So I'm going to do a pattern classification problem using these vectors. So every vector, I try to find out, does it belong to the class A, or does it belong to the class E, or does it belong to the class U, and so on, okay? So it's basically a pattern classification problem. But remember, speech, it's spoken by many different speakers. There's many different kinds of surrounding noise, right? While I'm speaking, I might be standing in a railway station, there might be a train coming, whistles, people talking in the background, somebody some plate falls down, right? So there's going to be a lot of variations in the signal that we capture. And therefore, it's similar to how we write, right? So if I write hat, right? If you look at handwriting, hat is written in millions of ways. Every writer, right, has a different way of doing cursive writing. So if you do handwriting recognition, the A occurs in multitude of ways, right? So there is a variability in the written alphabet A. Similarly, there's a variability in the spoken phonemes or the basic sounds, okay? And therefore, to capture this variability, we use something called a mixture of Gaussians or a Gaussian mixture model, right? Just to give you an example, right? So if I'm looking at heights and weights, so let's say height is one feature and weights is one feature, and from a population, I get these heights and weights of many different, thousands of, measurements that I've taken. If it happens to have a shape like this, then I can say I don't know how to model this cluster, right? Or how to model this this variation in heights and weights across different users. But if you say I am allowed to use circles of different radii, right? Or or fixed radii, but different center points, then I can model this guy with using 4 or 5 different circles, right? And a Gaussian mixture model is essentially trying to model this variability in this multidimensional space by a mixture of Gaussian. So if you look at a one-dimensional representation, for example, if I'm looking at heights, right? Heights from let's say the red guy is the actual distribution I measure, right? Which is somewhat like this arbitrary shape of the cluster, right? So if I'm looking at heights of many different people, it might look like this. But if Gaussian is nothing but a bell curve, right? So if I represent it with three bell curves, the three bell curves that match, a combination of these combination of these bell curves that match this red line, which is what is of interest to me, might turn out to be like this. And that might give me some underlying information. This means that there are three population, maybe children, women, and men. And so the density looks something like this. So we can capture the height variations across population by using a mixture of Gaussians, right? That's one part. Then the other part comes to what we would have heard of as Markovian models, right? So for example, if I'm trying to predict the weather for the next 5 days, right? So you might have NDTV giving you a 5-day forecast, right? Our meteorological department itself might give you a 5-day forecast saying tomorrow is rainy, day after tomorrow is rainy, then cloudy, sunny, sunny, cloudy, right? How do we predict these patterns, right? Obviously, it's a very difficult problem, but a lot of this is based on the assumption that I have, if I'm looking at data-driven approaches, I've seen what happened over the last 100, 200 years, and whenever one day was rainy, I try to find out what happened the next day. And let me assume that there are only three weather conditions that can happen. It can be either rainy or cloudy or sunny. Only these three patterns can occur. So given that one day is rainy, right, I can ask or find out historically from the historical information, how often did rainy happen the next day? How often did cloudy happen? And how often did sunny happen, right? So this is basically, given that I know rainy happened one day, what is the probability? That is the number of times rainy occurred the next day over the total number of times rainy occurred, right? Or number of times cloudy occurred after rainy and number of times sunny occurred after rainy, right? So these are the only three guys, so they all have to add up to one, right? They have to be in one of these states only, right? So this concept of states or events or being in one condition is basically where this idea of Markovian model and so on came. And if I'm going to depend only on the previous day, not the previous 2 days, then it becomes a first order Markovian chain, right? So this is the basic idea. And what we are looking at when given one day is rainy, the next day is cloudy, is what we call as transition probabilities in our models, right? The Markov models, right? So these are the conditional probabilities, right? Or the Markovian chains, basically saying that given this is there, what is the probability that the next day is sunny? So that is what we call as Markovian. But in speech, we have slightly different issues. So just to draw the analogy with weather, right? What can I observe usually, right? What I can physically observe is whether it was sunny, right? I can look out in the outside and find out whether it's raining or whether it's cloudy or whether it's sunny, right? But if my question is slightly different, I want to find out the pattern, whether there's a high pressure in the atmosphere or low pressure, right? High pressure essentially means there's the pressure is high, therefore air has to move out, right? It has to equalize, so it will go towards a low pressure region. So whenever we have high pressure, you tend to have sunny weather, right? On the other hand, when it's low pressure, air comes in from other regions, right? So there's a mixing of cold air, hot air, and so on. So it can lead to cloudy and it can lead to rain and so on, right? So if my task is not to predict the weather, but my task is to find out whether today high pressure is there or low pressure is there, right? How do I know? I can't. I mean, I'm all that I have is access to the weather pattern outside, right? I don't know how to measure high pressure or low pressure. So what I do is I look at the weather condition and then look historically what happened. Given it was high pressure, how often did sunny weather come out? Given high pressure, how often did rainy come about? This is called an observation probability. And also, I talked about transition probability. So that's happening here also. If it's high pressure, how often did it go to low pressure, which is 0.7? And in this case, there are only two states. The other one will be 0.3, staying back in the high pressure, right? So these are hidden from you, right? You cannot see it. You try to predict this guy based on what you observe, right? And therefore, we have this concept of hidden Markov models, okay? So in speech, that's essentially what's going to happen. What I observe is only the speech waveform. So if I observe the speech waveform, I can get waveforms from like this, and from waveforms I can get speech vectors, MFCC or MEL filter bank, but I don't know what was said. I don't know what the underlying phonemes are. Okay, so the task is very similar to speech recognition. Here I get only the MFCC or the MEL filter bank vectors, and my task is to find the underlying phonemes that produce them, which is basically the R, the E, so on. Okay, and so this is essentially what is speech recognition. It's a hidden Markov kind of a process, right? Where I'm trying to given the feature vectors, I'm trying to predict the underlying phonemes. Okay, so this is the first step. So given speech signal, I try to find these phonemes. As I said, there are only 40 or 50 different sounds. From phonemes, I can then create what's called a lexicon to get words. And from the words, I can create sentences by using a language model. Okay, so this is the lexicon, right? So I don't know if
It's fun to recognize speech.
so if I played that, my phoneme sequence will come something like this, right? And then I go and see, if the sounds E, G, Z, E, M, P comes, then I have a lookup table basically, which says if these sequence of sounds come, these phoneme sequence come, then the word is example, right? If idea comes, then the word is I, D, E, then it's idea. So from the phoneme sequence, I form words, and from words, I'm going to use a language model to basically form a sequence of words, right? Many phoneme sequences can sound similar, right? So for example, here,
It's fun to recognize speech.
Can some of you predict? So if I didn't know anything about the language, right, it's difficult for me to find out what was said. It's possible that I also said it's fun to wreck a nice beach. Okay, both of which will have the same phoneme sequence. Okay, and it's therefore important for the language model. Historically, if you look at what has happened in English, let's say by looking at all the Wikipedia pages and all this, you will say that this is much more relevant. This is what was spoken, and therefore I will output this. Somebody might purposely break the system by saying this. Remember, speech recognition is a probabilistic kind of framework. If somebody wants to break the system is going to make some mistakes. Okay, so there is nothing that you can do about it, right? But by and large, we know that people mean this often, so we are going to recognize this. So if you look at speech recognition, the task is very, very simple. Okay, first, given the MFCC vectors, I find the phoneme sequence. Given the phoneme sequence, I basically use a lexicon to find out the words. Given the words, I go and see which one, if I have two competing sets of words, right, which one makes a more meaningful sentence, and that is governed by the language model. Okay, so these are the three components. Okay, and here is a representation that we often use for speech. This is what we call as an HMM GMM model. Okay, so what do I mean by an HMM GMM model? So if you look at this top, this is my speech signal. Okay, and basically, there are two ways that I can do this task. One is I am training this model. So remember, I said historically I have to look at how often rainy occurred after rainy, how often cloudy occurred after rainy. That's this kind of transition probability. And then I have to find out the other one, which is called the observation probability. That is, given high weather patterns, high pressure patterns, how often was it sunny, how often was it cloudy, and so on, and rainy. So that's called the observation probability. So this I'm going to find from historical data or train the system, right? Training means using the truth, the ground truth, because I've already measured and I know what the ground truth was. I try to get all these probabilities, right? And that's one part of it. And therefore, to train the system, these are called the states of the hidden Markov model. In our case, these states, instead of capturing rainy, sunny, cloudy, these are going to capture the different phonemes, right? And the phoneme has its own transition probability, going from this phoneme to another phoneme. That's one which is called the transition probability. And each of these phonemes is like a high weather pattern. How probable is it that it generated this particular observation, the MFCC vector or the filter bank vector, right? So this is basically going to be your observation probability. Given this sound is na, what is the probability that it generated an MFCC vector like this? So this is what we are going to learn in the training part, which is called basically the training of the hidden Markov model, the training of the Gaussian mixture model, hidden Markov model. And during testing, so during training, I have to know that so training means I know the ground truth. Training means, so I don't know if you can see a dark line here. The first O1, O2, O3, there's a dark line, which means it belongs to the first class, in this case, silence. O4 belongs to the class na. O5, O6, O7, these are all MEL filter banks. They belong to the sound O. And again, the last features belong to silence. So this is called an alignment. So I have to know the ground truth, and I do the alignment, which is actually difficult. We have to do some automatic ways to do that. And then I estimate this probability given this alignments. Okay. And when I'm doing recognition, I don't have this alignment. The whole idea is to now, given the sounds or the filter bank, I identify these trained networks to output this sequence of classes. Okay. So that is what we mean by recognition part, where I get an output which looks like this, a sequence of phonemes. Okay.
But these classes are, it won't be like a clique. Every class, we can't jump to all the other classes.
Say that again.
I'm saying the phonemes, right? The relation between them, it won't be like from any phoneme I can go to any other phoneme.
No, no. So this is called a left to right model, right? So from speech, we know that if I'm saying the sound no, right, first na has to occur and then o has to occur. So it can't go in the opposite direction. O cannot come first and na cannot come second. So I can't allow any state to any state transition. So it's only left to right, what we call the Bakis model. Okay. So it goes in only one direction.
So whenever we build an HMM, normally for speech, we build a left to right model, sir?
Correct.
Okay.
And you will see the same thing happen in many places. So later we'll talk about something called connectionist temporal classification. That's also left to right model. Okay. So yeah, you're right. So it's only a left to right. It can't go from any state to any state.
And so we'll have a different model for every word in my vocabulary, is it?
Every sound, right? I see words, there are billion words I can have, right? But sounds are more, smaller set, right? There's only 40, 50 different sounds, right? So actually we do something called triphone modeling. I'm not going to go into that, but the numbers are not more than 2,000, 3,000, 5,000, that kind of thing. Okay.
Okay. So we'll have like 2,000 copies of this kind of.
To each one of, in fact, if you look at basic sounds, they're only 40, 50, depending on the language. But if you look at handwriting, right? So if I say hat versus rat, right? The A changes slightly depending, because when you do cursive writing, right? Nature makes it always easy, takes the easiest path, right? So therefore the shape of the A, when I write hat and rat, the same person, will be slightly different. So what we do is we take what's called context dependent modeling. And so we have phonemes and their variations. So that variation turns out to be about 5,000, 4,000, 5,000 variations. So we have separate models for each one of those 5,000 variations. And each of those states are modeled by a mixture of Gaussians to capture the variability, this variability, because of speaker, noise, and so on.
Yeah. Thank you, sir.
Yeah, this is a good time, because I think I will switch now to what's called deep learning, right? I'll come to that. So this is a good, I need some feedback. So is this very superficial? Some of you could understand. So basically there are 3 or 4 tasks, that's all. First, we have to recognize the phonemes. From phonemes, we recognize words by lexicon, and from words, we get a sequence of words which make meaningful sentences, and that's by the language model. Okay. And language model is something that you see all the time, right? So for example, when you're typing on your keyboard, right, how does the next word prediction happen? It's essentially a language model, right? It's predicting the next word, right? So because it knows these are the kinds of things that make meaningful sentences, we use language model, or your autofill on Google searches, right? So it's basically using what you have typed plus your history, of course, what you've been doing, but all of these are fancy language modeling aspects. Okay, so I just wanted, I'll switch. I don't want to give any demos because it may take too much time, but essentially, sorry, this is not, I wanted something, somebody has changed it. Okay, so I wanted all the consortium members, we had a nice graph, but that has been taken completely off. Okay, so I apologize, but what I wanted to say was, here, my student, I think by mistake changed the slide. What I had was a slide that showed almost 10-12 institutions, right, involved in this Mandi project, right? And they had it was a collaborative effort, community effort, right? And we tried to build systems in 2014-15, a good system that worked very well in the field with all the noise and all. This was for farmers and so on, right? We tried to build in 12 languages. Professor Prasanna was involved. I think Deepak was then a student. Professor Samudra Vijaya was involved. Many Professor Rohit, many institutions were involved, and that's where we are doing this summer workshops, right? And it was a collaborative effort, and we built many languages. And I'm proud to say, during the same time, there's a big company called Nuance, right, which came up and tried to set up the same thing in India, right? And that's when we realized it's very difficult for the government to use unless some startups get involved and take this to the ground level. Even though our system worked better than Nuance, okay, but somebody has to maintain. As an academic, we are not in a position to run enterprise level software, hardware, and so on, right? So the transition had to take place only if we had a good ecosystem, and that's when this idea of and actually being meaty, right, they wanted this projected. And this President Modi, PM Modi gave a speech where he talked about the project and said, okay, something like that, right? So the important point that I want to make is, it is a community effort, right? We have been trying to build communities, right? Unfortunately, last 4-5 years, I also had personal problems, so my focus was off. Many of us had to deal with other things, so the foot was taken off the pedal, so to speak. But I think, again, people have got excited about it. I think this is a cusp. And in terms of technology itself, rapid progress has happened, as I'm going to speak in the next 1 hour, in the field itself, right? And speech first took off. We have been working for, I have been working for 32 years, but speech took off only when Apple came up with Siri in 2011-12, when we saw first commercial kind of usage, right? And the last 4-5 years is when the when the usage actually worked in practice. Still, I'm sure most of you don't use Google Voice, right, to call home or call Dinesh or call Deepak. You don't do that. But I think it is only because we are not used to it. But once these things work reasonably well, right, it is there, right, for many applications. It makes more sense to use these systems, right? Some of the other applications people may not find use, but as the system becomes more user-friendly and robust, you will start using speech. It's going to be much more convenient than typing, obviously, right? And your mouse and your keyboard and your touchpad, these are all things that you have to master. And people like my parents, my mother, if they have to use it, there's no way they can master this. I cannot master many of what you youngsters can master, right? As we grow old, our connections, we'll see the neurons, right? It's not that good, right? So it's going to start making some mistakes. So it's difficult for me to make new connections, right? So what is happening in the world of ASR today, right? So what I talked about is what we call as a conventional GMM-HMM system, Gaussian mixture model, hidden Markov model, right? This still has value, right? In today's world, we still need we still need this. Okay, if we don't have this, we are not going to build small systems which are not data driven, right? So if I want to only do digit recognition, GMM-HMM is more than enough, right? So one thing I want to say is don't use a machine gun to kill a mosquito, right? So just because you get hold of a machine gun, which is what this guy is going to be, right? Just to kill a mosquito, you should know what to use. Be aware of what the application is and use things appropriately. Okay. So what is the problem with the conventional approach? The conventional approach needed what's called the acoustic model, the lexicon, and language model. The acoustic model is where the the computer science, the electrical engineers, these physicists, and all of these guys came. The lexicon is where you convert from sounds, which are basically what we call as phonetics, right? Phonemes. So this is where the phoneticians, right? The whole group came into picture. And then the language model is what we call as linguists, right? The language experts. They came into the picture. So any good speech recognition system in any lab needed all of these experts, right? And so we basically had to have a huge team to build good speech recognition systems. Okay, all that changed in the last 4 or 5 years, right? So we have what's called end-to-end speech recognition systems, where you give a waveform and out comes a text, right? There is good and bad in this kind of a framework. The good part is it's democratizing a lot of this, right? So even today, next week, when we do this, you will be able to produce very good outputs, in fact, competitive outputs to the rest of the world, right? Because you're riding again on many people's shoulders. Many people have written free software, open source software. So we have amazing contributions right from the day of Kaldi, before that Sphinx, before that HTK, right? So we had actual people, working, from universities who actually shared all their knowledge. So today, speech recognition is taking off because first, this HDK, Sphinx, and Kaldi came. Kaldi is a game changer. Dan Povey made a big contribution to speech. And then ESPNet is a variation because Kaldi struggles with neural network kind of framework. So ESPNet is another free open source software, and they have so many recipes, right? And then you have Google itself sharing, and Facebook, AI sharing their FairSeek codes. You see, we are riding on many people's shoulders, right? And when you get this, there are two parts. One is, suddenly you feel you can achieve a lot of things, and that is very exciting. And that's how youngsters should be. I want our generation, can do, I can deliver. That kind of attitude, right, should come, right? But then arrogance should not come. The arrogance comes when you do one and it works, right? And you see you have solved the speech recognition problem, right? That is a mistake, right? Because if you run into the slightest of problems, if you don't know what's happening here, if you can't generalize, if you can't go to new domains, new data, come up with new ideas, new techniques, you can't, this technique will be old in another 1 or 2 months, 1 or 2 years at least, right? So things evolve, right? And you have to keep up with change, right? And that's a constant learning. And unless you understand what happens, you are not going to learn newer things. Okay, so this evolution is important, that you keep learning, right? I learned today, I don't know many things that you people know, right? I mean, PyTorch, I have, all these things are very, very important tools, right? And I keep saying speech recognition rides on many things. 20-25% is the knowledge, but another 75% comes from other sources, right? Including implementation, coding, and so many aspects. Okay, so all that I'm saying is I want this democratization to take place, but appreciate that you also have to go in depth. Don't get too overconfident once you do something simple. Okay, these are what we would say toy problems. I want you to deliver really hard problems and make it work, right? And that's where I hope this workshop will get you to that place. Okay, so what is the basic idea in all of this? So the revolution took place in what we call as deep neural networks, right? Neural networks have been there again for ages. So every 10 years, it'll become, in mid 80s, we all got excited about speech, neural networks. Professor Yagna Narayana was one of the forefront, but it never could compete with the commercial speech recognition systems. Again, the mid 90s, it took off. Harvey Burlard and all these guys, Hinek, so many guys have contributed. It never took off. It's only after 2008, and Hinton, by the way, was this amazing guy, right? You pay Hinton, millions of dollars now, but he had these ideas from 86 actually, and he's been persevering. So there's this famous quote that when Hinton used to come in the 1990s and give a talk, that talk will have only 4 or 5 guys because no one believed in neural networks. So I invite Hinton to IIT or IIIT Hyderabad, Dharwad or something. Nobody has heard of Hinton, right? Some USS guy talking about speech neural, right? He didn't know much. He didn't do work in speech neural, right? He worked more on neural. People didn't appreciate what he was doing, right? And today he's a Google fellow. He has $1 million. Now he will charge you, just to give one lecture, thousands of dollars. I mean, he just doesn't have the time, right? So it's good, right? But I think what I'm trying to say is things evolve, and you don't know when some old things will actually take shape and become exciting new field. Okay, so artificial neural networks have been there for long. Deep neural networks actually hint this whole idea of pre-training is what energized this whole field, right? And so today you might not be willing to listen to somebody who's just because he's not hot, but the same guy, I'm happy that researchers like him have got what they, because they persevered for almost 20-25 years, and then they got their due, right? So but then there's another guy called Schmidhuber, who's never recognized even today, because this trinity in Canada dominate, but Schmidhuber's contribution is even more enormous, right? The LSTMs are there, and that's why we have working systems, right? But we don't know who Schmidhuber is, right? None of you know, but many of you might have heard of Benjo and Hinton, right? So the point is that things evolve, so don't get arrogant, right? Be always learn, be modest, try to learn, right? So where does this concept of artificial neural networks come, right? So basically it's inspired by our own neurons, right? I mean, as I said, our brain is a supercomputer, right? And basically there are inputs to this body, right, to this axon, right, which basically is some stimuli coming from other sources. Then this guy gets energized. If the stimulus is not sufficiently strong, this axon will not do anything. But if it's sufficiently strong, then it will fire. You get this firing, right? And then it fires, and then these go to other bodies, right? Cell bodies, right? And so it gets fired once in a while when there's sufficient strength in the stimuli. So we approximate this idea by having two components in a neuron, which basically says I take some inputs, we take a weighted combination of those inputs. So this is a linear combination of inputs. So essentially it's a linear processing. I don't take square of this or do any of those, right? So just the simple input times the weights, and the weights determine how much importance I'm going to give. So this is still a linear processing. The beauty of neural network comes because of the non-linear, this activation function, right? So I put a non-linearity at the output, right? So my Z, which is, if I look at the neuron and divide it into two parts, one part is just doing linear processing and generates a number, right? If it is W1x1 plus W2x2 plus Wn(xn), I get a number, right? And that number, I'm now going to non-linearly. So the number I'm going to plot along the x-axis, and along the y-axis is the output. So if the number is less than a certain value, a threshold, I give 0. And when the number is greater than a threshold, I give a 1. Okay, so this is basically a non-linearity. Why do you say it's not linear? Like it's not a line, right? So it abruptly changes this thing, right? And this is the reason why neural networks work. Okay, so this non-linearity gives it that benefit. Okay, but we don't prefer such harsh functions suddenly changing from 0 to 1. We need some more smoother function, because we will use something called derivatives to do what's called backpropagation of errors. And so to take derivatives, I need some smooth functions, right? And so we use sigmoid, and you might hear about tanh, ReLU, and so many other things, right? So these are all non-linearities which give the power to a neural network. Okay, and it need not be a single neuron. It can be a collection of neurons along one horizontal plane. So that's called the layer. And I can have one more layer here and one more layer here, multiple neurons, or one neuron, or two neurons. I can have many layers. And there is a formal proof to show that as I go and increase the number of layers, right, it's the whole idea is to do pattern classification, right? If I want to identify the different sound classes, right? So basically, if I have only two patterns, A and B, and these are the two classes, so B class here, B class here, A class here, A class here, there is no linear separable boundary, right? I cannot separate the two categories A and B by just one line, right? And so with a neural network, as you have more and more layers, you can have complicated decision boundaries, okay? And that is the power of a neural network. So I can do much more fancy pattern recognition, pattern classification problem, even when the classes have a very non-linear decision boundaries, okay? So what is the basic idea in a neural network? I have some inputs, right? I'm going to take weighted combination of the inputs, then pass it through non-linearity, right? And so to do that, I have to know what these weights are, and that's essentially what we mean by training a neural network, right? So I need to know what these weights are. I might know what the input is, but I don't know what the weights are. And I should say that these slides are essentially borrowed from Professor D.W. Corney's slides. Okay, so weights are important. I don't have time, so I'm going to skip this. In nature also we have weights, right? I was about to talk about how vertigo affects people and so on. So again, sorry, I just made slides in the last moment, so there are some things. Okay, so let's say that I'm going to use a neural network for pattern classification. So in this case, let us say I'm going to use a neural network to identify whether a person is diabetic or not. Okay, and to do that, I need to make some measurements. So let's say I take his glucose level, I take his body mass index, I find out his insulin. So for the first patient, let's say the glucose is this much, the body mass, it should be in 2734, but anyway, and the insulin level is 1.9 or something, right? And I need historical data, right? This is how we can train a network. Remember, when I'm talking about weather, I needed 100 years previous information to get what I can predict for tomorrow, right? So similarly, I can train a neural network if I have some historical data, right? So I know that for this patient, the doctor diagnosed him as 0, which means he does not have diabetes. For this patient whose measurements were this, also the doctor said he's not diabetic. For this patient, the doctor said he's diabetic. So I have measurements from thousands of patients, right? So where I make these measurements and I have these classes. Now, tomorrow, if I can get these 3 measurements, so what do you want to do? You don't want a doctor to spend all this time, or you want to go access people in the villages who might not have access to doctors. Can I automate a system which at least will warn if a person is diabetic or not, right? So I have to build a system. So what am I going to do? I'm going to give this input, right? I'm going to train the system. What does training a system mean? It essentially means I'm going to learn the weights, right? So for learning the weights, I'm going to use what's called supervised learning, right? I know for these 3 guys measurements, this guy was 0 class, that is no diabetes. For these 3 guys, it is 0 diabetes. For these 3 guys, it is a category 1 or diabetes. So I'm going to train an automatic system so that now when I give this, it will correctly say whether the person is diabetic or not with a high probability. It's not going to be 100% correct, right? But it's going to work most of the time, right? So that's essentially what we mean by training a neural network. So let's say I randomly put some random numbers for the weights, right? And I feed the first guy, right? This is my input, right? And these are my hidden layers, right? And now what should be the output? Because I'm training, I know what the output should be. The output should be 0. But because I randomly put some weights, my output will actually turn out to be some other number, 0.8, for example. So it has made an error, right? So and the expected output is 0, but I got 0.8. So I make an error. And how much is the error? The predicted value minus the actual value, which is 0.8. This is called the loss function, right? So we don't use this kind of loss functions. You will see that you'll use something called cross entropy and so many other things, okay? But now what should I do? After knowing that I made such a big mistake, I have to go and adjust the weights, right, to reduce the error, right? So this, I do something by using something called backpropagation. And so if I do that many times, for this output, the network is training and becoming better and better. Now I expect 1, but it's giving 0.9, which is not bad, right? It's come close to 1 now, right? I expected 1, but it's coming to 0.9, right? It's small error of 0.1. And then I can keep doing it million times, right? This is what we call as training the neural network. We do multiple iterations, right? And if you go through the entire data once, we call it as one epoch, right? And so we keep doing this multiple times, and the network learns better and better. In fact, it's so good, it will be able to even get complicated boundaries separated. So if the diabetes guys and non-diabetes is like this, a normal linear classifier cannot do a good job, but something like a neural network can do a great job, right? So it's able to separate some complicated classes that are separated like this, right? And as somebody said, it's a dumb algorithm, right? You do it to many times, and actually it's lucky that we get something that's effective and works most of the time, right? And that's why the idea of pre-training and all that was important. But with a lot of data, we find that it does a very good job. It might not reach the global minimum, right? But it does hit a minimum local minimum that is useful in practice. Okay, and as I said, there are different types of loss functions, the mean squared error and cross entropy and so many all things. Okay, one of the things I wanted to point out was that we are going to use a concept called softmax, and this is very, very useful in many parts of what I talk about later, right? So I'll quickly talk about it. So again, let's say I have in the previous example, right? I had a two-class problem, right? I had only diapties and no diapties, right? So there are only two classes that I had to worry about. There are only two classes, right? But I might have applications which are multi-class problems, right? I might have multiple outputs, or I might need to classify among several outputs, right? So for example, I'm trying to recognize spoken digits, right? So I am allowed to say only one of those 10. I can say either 0 or 1 or 2. So 0 to 9 is actually 10, right? Because 1 to 9 and then 0 is there. So there are 10 different classes that will be here, right? And then I give a waveform which will be one of the spoken words, 1 or 2 or 3 or something like that, right? So given this waveform, now I'm doing actual speech recognition. I want to output whether 1 was said or 2 was said or 0 was said or 9 was said. So there are totally 10 different classes, right? So at the output, so whenever I say 1, only the first guy should light up. Whenever I say 2, only the second guy should light up, right? All the others should be 0, right? So this is a multi-class problem. So what I do is at this output, I do something slightly different, which is the idea of softmax. This is called logits, right? So I take e to the power of whatever this value is. Now, e to the power of z is always non-negative, right? If you have e to the power of minus infinity, it is 0. E to the power of 0 itself is 1. E to the power of plus infinity is infinity, right? So it's always above, it's non-negative, right? It's always going from 0 to infinity. So this number is non-negative, right? So similarly, e to the power of z will also be non-negative, non-negative, non-negative. Now I add up all of this guy and put in the denominator, right? Because I added all non-negative numbers, this guy is also going to be non-negative, right? Now, this is the addition of all of these e to the power of zi's. So if I take the first one divided by this guy, obviously in the denominator, this term is there, plus some some positive terms are there, right? So this guy is a non-zero term, which is also here, a non-negative term, which is also here, plus some other positive quantities are there. So these guys will add up to a quantity more than this. Therefore, the ratio is always going to be positive because these are all non-zero and less than 1, right? And if I add up all of this, the denominator is just the addition of all of this. When you add up all of this, you get the idea of, they all add up to be, numerator will be same as denominator, so it will become 1, right? So this is essentially the idea of this e to the power of zi by this, which is called softmax zi, which I'm calling as yi, right? So yi is always going to be between 0 and 1, and the sum of yi's is going to be 1. Okay, so what kind of what does this remind you of? Anyone? Can you say in the chat box? This reminds you, so these guys can be between 0 and 1, right? So it reminds you something like probability, right? So this is essentially what we're trying to mimic, right? So if I get 0.9 for a particular guy, right, the total has to add up to 1. The others 0.001, others 0.002. So let's say Z3 becomes 0.9. That means it has a 90% probability that it's this guy. So whichever is highly probable, it is that guy that I'm going to say as the output. Remember, this is all probabilistic. I will make mistakes, but I have to reduce the number of mistakes that I make. And if I make a mistake here, I'm going to backpropagate and I'll just wait so that I keep reducing the error, right? So this idea of the softmax is very, very important. And I can use that. We will see later. What if this class has, here I had 10 classes, right? If I had 10 million classes here, right? Then what happens? Then it becomes much more, we don't want to do it. First of all, I have to compute all this, if I have 1 million classes, I have to compute all of these 1 million guys. And that's going to be, we will see that this is what is happening in what we call as word to vec, and later on in what's called contrastive predictions and so on, right? So we have to simplify this. So we'll use the concept of what's called noise contrastive estimation. So I'm not going to take all of them. I'm going to look at something called the distribution and take some negative samples that will definitely compete with this guy, right? So this idea is therefore going to lead to this concept of noise contrast estimation and things like that, right? Negative samples and so on. Okay, so basically this is essentially what I do. And I said that I'm going to adjust the weight, so I'll just give you an idea why the derivatives are important. So if I had only one weight, right, and my error was a function of this weight in this particular fashion, right? So where is the minimum error? The minimum error is when the weight takes this value, right? But I don't know what this optimal value of weight is, right? Because if I'm looking in a multi-dimensional space, there's no way I know how to find the optimal. I can't even visualize this error curve, right, in this multi-dimensional space. So that's why we randomly initialize the weights, right? Can do something smarter, right? But pre-train is one of them, right? But we randomly, let's say, randomly initialize here, right? Then which direction should my weight move to reduce the error, right? If I look at this guy, the weight should move in this direction to minimize the error, right? If I had accidentally taken this as my initialized weight, then I should move in this direction to reduce the error. So what we do is called the weight update. So we take the a random value of weight and keep make small adjustments to the weight such that I reduce the error, right? So to reduce the error, I have to know which direction to go, right? So basically, what am I doing? I'm taking old value of weight and I'm going to take a small quantity and either add or subtract this and get the new quantity, right? That is called the weight update, right? And there is this concept of learning rate that you'll see. But now, which direction should I know is not obvious, but that's where the beauty of this derivative comes. If you look at the slope here, if my weight was here, right, the slope at this particular point is negative, right? But I have to move in the positive direction, right? I have to move towards the positive x direction, right? So it's always a negative of the slope that tells me which direction to go. So if it's negative will give positive, so this quantity will become plus, so I will move in this direction. If I'm here, right, the slope is positive, right, and this is my initial estimate, I should move in the negative direction, right? And that's essentially this is positive, so then the sign remains as it is, so I'll reduce the weight, right? I'll go in the towards 0, right? So that's the basic idea of gradient descent, and what we call is, we do multiple things, back propagate and so on. And the reason why we choose the tan H and sigmoid is the derivatives come out to be in very neat forms. Okay, and as I said, it need not be necessary that I hit a local, a global minima. I might hit a local minima, but that's okay, right? In many applications, it does work. Okay, so this is the basic idea of a deep neural network. Why is it called deep? It's going to have many layers, right? So this is called the input, where I give the features like body mass index, insulin, and so on. This is my decision bound class output, right? I might say if it's only one, two classes, I'll have only one node, diaptic or no diaptic, or this might be the MFCC filter bank, speech vectors, and this might be 0 to 9 digit recognition, right? So I can do complicated things with a deep neural network, right? And so now I'm going to talk about specifically what happened in the next half an hour in the area of speech and deep learning. Okay, so if you recall, basically hidden Markov models had two components. One is what's called the transition probabilities. These capture the basic sounds, right? And each sound, because of the variability of the speaker, noise, and so on, is mapped by a combination of Gaussian mixtures, right? So remember, there's some probability that I've talked about, which is called the observation probability. So given that I am in this particular state, how likely is it that I could have generated a particular observation vector O1? And so basically I have to look at this GMM because it's belonging to the state, and look at the likelihood of this GMM generating this particular observation vector, right? So where does deep neural networks come? So how did the GMMs do? So the GMMs took our MEL filter bank. Okay, these are your frequency dependent. Remember, frequencies determine the phonemes. I go through a set of deep neural networks. These are all hidden layers, and at the output, I want to recognize only the phoneme classes. Okay, so that is essentially what we are doing here as a multi-class problem, right? The softmax comes, right? I talked about softmax somewhere, so it's a multi-class problem, and for every feature vector, I find out. So every feature vector, I find out what phoneme was there. So the phoneme can be 50 or 45 different phonemes, or if I'm looking at context-dependent phonemes, they might be at 5,000, right? So for every MEL filter bank, I try to find out which phoneme is most likely to have come out, right? So so the old way was done using the GMM, right? That's happening here, and I skipped one step, right? The new way is done by using a deep neural network. So that is this guy, right? So sorry, so I confused you guys. So one way is to use GMMs, right? The other way is to use a series of neural networks to give me the probability that this guy generates. So what we have done is replace the Gaussian mixture model with a deep neural network. I'm sorry, I just confused a little bit. This was a neural network, and somehow I confused when the softmax comes. So essentially, I have replaced the GMM part by a deep neural network, which will again give me scores that for given this guy, how likely it is to have come from the phoneme Y, right? So this, so we'll have to divide this by the priors and so on. But essentially, we are going to output some kind of a probability of a particular phoneme given the input. Okay, and that is essentially a transition from Gaussian mixture model to a deep neural network model. The hidden Markov part remains the same. Okay, so this is the first step from GMM towards neural network. The problem in training a neural network, remember, for every sound class, right, I have to, when I train, I give the input features, which are the MEL filter bank, and I tell what the output should be, right? And so in speech, that means for every MEL filter bank, I should know which phoneme it belongs to, right? Whether it belongs to the R sound, the E sound, the U sound, and so on, right? And therefore, I need something called alignment, right? So given that O1, O2, O3, O4, I need to know whether it belongs to the sound class silence, even if I'm not, even though I'm using a DNN here, right? I still need to know which class it belongs to so that I can get the appropriate softmax here, right? So, and similarly, the yes, no, yeah. This I have to find out which, from the from the waveform, I get the features, right? Every 10 milliseconds, I can find out that these three features belong to sound here. These set of features belong to sound eh, and these set of features belong to sir, and this belongs to silence. Okay, so this is essentially what we call as frame to state alignment, right? And I need, yeah.
Sorry, a participant has raised a question. Suresh, you can ask.
Yeah, please.
Suresh, please unmute and ask the question. Or you type in the chat box. Okay, sir. Proceed, sir. Maybe.
Okay. Yeah, please ask questions. Okay. I know I'm going a little fast, but I want to just get a big picture. Okay. So don't get too flustered if there's too much information. Just don't worry. I mean, if you get a big picture that there's something called phonemes, lexicon, language model, deep neural networks, right? Those kind of things is all that you need. And then when you do the next 2 weeks, you will start seeing this video will be available, right? I hope. And so you can keep listening to the video again and again, and you'll start seeing the connection between the things that I say. Okay. So
Sir, in the older model, when we were using GMMs and HMMs, we were not using GMMs to predict the phoneme, right? It was the other way. From phoneme, we were trying to see that which GMM model is most likely. While in DNN, this role has got reversed, is it? It has become a classification problem.
So it's basically, when I'm training the neural network, right? So basically, it's a parameter estimation problem, right? So there, it's likelihood that I'm going to learn, right? But when I'm testing it, it's basically going to now give me what's the probability of this guy belonging to this particular class, right? That's what I'm going to do. So remember, likelihood and posteriors are basically related to this priors, right? So there is going to be normalization or no normal. For example, DNN actually gives you have to normalize that DNN output to get the score. Okay, is that your question?
Say in DNN, of course, we are doing a prediction. We are calculating the posterior. But earlier we were maximizing the likelihood. Is it? That's the shift.
For training, yes. So essentially, when you're doing a training, we are doing it. For testing, we are again finding only some probabilistic thing. No, there is no likelihood is used when you're training something.
Yes, sir.
Yeah. Okay. So the way you could argue is if I'm looking at words, right? Probability of words given the acoustic sequence. So you can argue that I'm doing. So that in some sense is a likelihood. The probability of this particular HMM generating this particular sound observation vectors. Yes, you can talk of it as yeah. So is that the question? Yes.
Yes, sir. Sure, sir.
Yeah.
Thank you.
Yeah. But they're all closely related. Okay, that's the point I want to make. Okay, so where was I? Yeah. So this important thing called alignment that has to be done for DNNs, right? So if I want to do a DNN framework, right, I need to train the DNN. I need to know for each frame what class it belongs to, right? And that's difficult. I had to do alignment to get it, and the alignments themselves are not perfect, right? And that's where we started this new idea, which was actually proposed by Graves back in 2006. Again, I keep telling you, things don't catch on for a long time. So actually, Graves came up with this idea, Graves and Schmidhuber in 2006. In fact, ICHCAI was held in Hyderabad, and that's where I think the first time they talked about CTC itself. But the idea of CTC is used now, right? I mean, so popularly, it never took off until at least 2012, 13, so on, right? So 6-7 years after what Graves proposed, right? So so if you recall, this is what I mentioned. So if I'm replacing the DNNs, the GMMs with the DNNs, right? So essentially you're getting frames, right? And from frames you're going to get some classes, right? But from classes, these are phonemes. I still need a lexicon to convert the phonemes to words. And from words, I create a sequence of words to create the language model. Okay. So now the question comes, and this is where two things happen. One is I can output the phonemes as it is, right? And for phonemic languages, we see that the phonemes are very close to our written text itself, right? So this is where this concept of end-to-end starts coming slowly. So I could, do this pattern classification problem slightly different by asking, given this sound vector, feature vector, what is the sound that was produced? Or correspondingly, I can ask what character, written character this corresponds to. Okay, so now I'm going from spoken to a written, which is a big, there is a transition from spoken processing to something that's related to the written part. Okay, that transformation is not very big for phonemic languages like Indian languages, but it's very, very big for European, for example, English, right? So there is a slight thing that you have to worry about. So which is that I could output the phonemes as it is, but if I'm going to do alignments, right, and I'm not worried about the specific arrangement of which sound corresponds to which phoneme, but I'm only interested in a kind of a sequence to sequence kind of a representation, then I need not even output sir. I might directly output the characters YES. Okay, so there are two things that I'm switching here, gears. So be careful. One is I'm going to switch from not using alignments, and the other aspect is my outputs are no longer going to be phonemes. From phonemes creating using a lexicon to words and then language model, I'm going to directly output characters, and that's the basic idea of CTC, right? I could use CTC for phonemes also. CTC is a method that can be used for anything. So people started with phonemes, but then they quickly said, why go through this lexicon and all? I can directly output characters. Okay. So what is the basic idea of CTC? So given MEL filter bank outputs, right? I am going to look at the written characters that should come at the output. Okay, of the, and let's say there's a big neural network. This is the output of the neural network. Okay, now for every one of these, I know while I'm training, right, that it is the characters India that should come. And here again, it's a left to right. So first I has to come, then N, then D, then I, and again A, right? So it has to occur in this particular order. That's why we call it as a sequence, right? What does sequence mean? Sequence means there is a particular ordering in which they will occur. Okay, so therefore we need this ordering to be preserved, right? Now, given this sounds, if I'm mapping it to sounds, that the sounds can occur in different durations, right? So somebody might say India, and then I will be stretched for a long time, right? Somebody might say India, right? So D can get stretched for a long period of time, right? So when you see sounds, you can see that it can map to different durations in some sense, right? And therefore, even though there are 10 observation vectors, the partitioning in which it should happen, whether the first two should be II and then NN and DIA, is not clear. One way I can do is by doing a forced alignment, right? In which case I need to do this alignment by using another model like a GMM HMM, right? So one way to do is to actually find the alignment and do this aspect. Or you can say that I'll take all possible alignments, right? And then take the sum of all those probabilities. And that basically we can do something quickly by using something called the forward backward algorithms, right? And directly output the characters India, okay, INDIA, okay? So this is the basic idea of CTC, that it does not need a frame to state alignment. It does not need at every point for each vector to make a decision whether it belongs to Sir, or it belongs to year, or it belongs to and so on, right? So this is captured indirectly through the softmax, right? And we are looking now directly at a character output, right? So already now I'm moving from I've still not got the language model into play, but I've sort of got rid of the lexicon, okay? So because lexicon, again, I need an expert phonetician to tell me for every word how I have to expand the sounds, right? So this is basically what CTC is all about, right? And as I said, Graves, sort of proposed in 2006, but it sort of caught on after 2011, 12, I think, and then he came up with RNN transducers and so on, okay? And
this work, we will need multiple combinations of, or multiple kind of character alignment, right, for this to work? Like
correct. All possible alignments, correct. With the last, of course, it has to start with I and end with A, because we know India set.
Yeah, but I to keep for how many times we don't know. Like do it one time, 2 times, 4 times.
We do it for all, and for each one of them, we find the probability. So see, if I take an alignment like this, for example, right? So here, what did I do? Here I forcibly said O1 belongs to this in certain thing, right? So what is happening is these are what we call as the states, right? Now I'm going to replace the states by not sounds but by character. So it is basically these guys are along the x-axis. This will come along your y-axis, and I'm finding out all possible paths instead of forcibly aligning that these guys will belong to this, I'm now going to take, this guy can belong to even this guy with some probability, right? With a very little probability. So I'm going to take all of those alignments, right, and add up by using something called forward backward. So it's going to be basically, if we will see later, it's some kind of a traverse through the states. Now the states have been replaced, the sounds have been replaced by characters. So these are now going to be vertically put down, right? So we'll get silence, Y, E, S, and silence or blank. And then we go along the path and find all possible alignments through the paths. I'll show it and add all of those probabilities. Does that answer your question?
Yes, sir. Thank you.
Okay, so it's going to look something, so I'll come to that part. It's going to look something like this. So we're going to go through all possible paths, okay? But what happens is that when I'm decoding, right? When I'm decoding, I'll get, all these alignments. What I'm going to do is, to get back India, I'm going to merge all consecutive characters until I hit the next character. So I see this is the same character, and then character changes. So I merge all of this to one character. then again I get AAA, so I merge all of this to one character, right? So if I have NN, then I change, so I merge these two, then I go DDDD, I merge these two, and then I merge these two, and that's how I get the unique India, right? But there is a problem if I have repeated characters, right? So for example, if I have SS, PPP, now because E and E occur twice, I don't know if it's the first E that is here or the second E that's here. There's no way I can find out this thing, right? And so if I collapse it to one E, I'll get spec as the output, right? Not speech, right? So therefore, Graves, it's a very trivial way of very smart guy, right? So Graves said, I'll use an extra symbol called blank, right? Which also is used when it's not confident of any of the outputs, right? And so what he does is between every character, he starts putting blank. Okay, then making sure that two consecutive characters that are repeated should necessarily have a blank. Okay, therefore then it becomes very easy. So this is corresponds to the first T, then necessarily it has to go to a blank to go to the next T. That is the constraint. So this E, if it's repeated, has to necessarily go to another blank before it comes to the E. Then you will definitely get speech as it is. Okay, so this is basically why the blank symbol gets introduced in CTC, right? And as you asked me, so this is what we call as the the traversing path. It's almost like a Markovian process, right? So these are your states. In this case, the states are mapped by the letters, and the MEL filter banks O1, O2, O3, all of them, they are going along the right direction. So for every frame, I make a decision. For every frame, I make a decision whether it's fur or E. I mean, in this case, I'm talking about characters. So F or E and so on. Okay, and there are certain rules for traversing this path. So if I'm at F, I can go to F again, right? I can go back to a previous character. I can go to the same character. I can go to a blank, and I can go to the next character. Okay, so between any two characters, I'm going to introduce a blank. Okay, so for F, I can go to F, I can go to blank, and I can go to a next character. But if I find, for example, in this E can go only to E can go to a blank, but E cannot go back to go to a next E, the same character. Okay, so this is not allowed. This path is not allowed. So we put some constraints, and essentially that guarantees me that once I hit the first E, I have to go through a blank before I hit the next E, right? And that's how I guarantee repeated characters can be collapsed into unique representations. Okay, so this is the basic idea of connectionist temporal classification, or CTC, and you will see that CTC is one of the criteria that's used, right? We will come to something called transformers, but you can basically, and this is done by forward backward algorithm. A special case of that is Viterbi and Max setup. Okay, so in many of your outputs, you will in the course of this workshop, in many cases, what you will be doing is you will be taking the MEL filters, right, or a fancier version, maybe doing some kind of representation learning and outputting only characters. Okay, and that is what you're going to do. Because you're using characters, you need a powerful language model. Okay, so that is something that you will see. You can get rid of the lexicon, but you still need a powerful language model. Okay, so now yeah.
Sir, how do we determine the boundaries between two E's?
I told you now, so you're forced to go through a blank.
But how do we determine where if we have to put the blank after two E's?
No, we put after every. This is basically a algorithm, right? So between every character, I'm going to put a blank. Okay, I'm going to say that from this E, I cannot go back. So I'm going to put path constraints, right? From E, I cannot go to a previous character, right? From this E, I cannot go, or from this T, I cannot go to this E, or I cannot go to this E, or any of this. So what are the constraints I'm going to put? Any character, the next step can go back to the same character, can go to a blank, or go to the next character, as long as the next character is different from this character.
Okay.
Clear?
So how do we know that the first E is different and the second E is also different?
you know what you're going to out. See, everyone is a state. You're only, there is, see, there are two parts. One is an alignment, right? One is while training, right? While training, you know what the output should be, right? So you know exactly whether this C is different from this C, right? While training, correct? While testing, now if while testing, I'm going to get softmax basically, right? So for each part, I'm going to ask, if you ask me if this character is going to go to the next character, which will again be outputted as E, I will not allow that path. It has to go through a blank. Am I answering your question?
Yes, sir.
Basically it's all probabilities, right? So if my probability of the next character is the same as the previous character, right? Then I'm not going to allow that path.
Yes, sir. Understood.
Okay. Okay, so in deep neural networks till now, we have been doing, for every frame, I make a decision boundary, right? But that's, in many applications, that might not be a good thing, because I might want to know what is the history or the memory, right? So basically, that's where the concept of recurrent neural networks come, okay? So in recurrent neural networks, it's essentially nothing but a feed forward like this, okay? But what I do is, when I'm feed forwarding, the let's say the first feature comes. When the next feature comes, I take the output from the first feature and also feed it back. Okay, so there are two inputs in recurrent neural networks. So if I remove in a recurrent neural networks, if this was the first feature, I'll go through, actually this is this complicated diagram here. So there'll be many nodes here, many layers itself possible. And this is the output layer with many nodes. And each of those many nodes to many nodes is done through a matrix, right? So the weights, right? This is called the weight matrix. And again, many nodes to the many nodes output is done through the V matrix, weights V, okay? In a recurrent neural network, in a feed forward, for this feature, I'll go forward, right? The next feature comes, I go forward, and there'll be no connection between the two features. So this feature independently does this. The next feature comes, it does not know what happened before. So it independently does. The next feature comes, it goes directly without even bothering what happened previously, right? So there is no information about what happened in the past. There's no memory or history, right? On the other hand, in a recurrent neural network, the output here is fed back here, right? So when I'm giving the next frame, I'm also getting some information about the previous frame through the output of the hidden layer, right? So this particular guy is not only having information about this guy, it's also happening information about what happened previously. Now, when I come to the third frame, this is determined not only by the input in the third frame, it's also influenced by the input that's coming from H2, but H2 itself is influenced by X2, right? And X2 is influenced by H1, so X1. So this Xn is now having some information about what all happened previously, right? So there is a feedback. That's why it's called a recurrent neural network, okay? So therefore, if I'm saying 9, right? So sound 9, na, I, then if I'm only doing digit recognition, there's a very high probability that this, I'm going to say na, but it also gets some information that first two were na and E, right? If I'm looking at sound classes kind of thing. And so that's also going to help me get 9 better here. Okay, so that's the whole idea of recurrent neural networks, that the history helps you a lot. Okay, this each one of this is multiple nodes. And remember, this one node has many summations and then a non-linearity. But these guys have this problem, what's called vanishing gradient or exploding gradient. So Schmidhuber, Alex Graves' advisor, and the other guy, I forgot, Santiago or somebody, they came up with this idea of LSTM, right? Which is basically a more fancy node. Okay, each node here is replaced by this fancy with pass-throughs and gating and additions and multiplications to make it more robust to prevent vanishing gradients and exploding gradients kind of problem. Okay, now I'm going to say why recurrent neural networks are important, especially if you look at from a language modeling perspective, right? So if I have the words the cat, right? Then I want to know what is the next word that is said. Remember, this is exactly what your keyboard typing in your mobile phone is doing. It's going to predict, it's going to anticipate. Of course, it also keeps a history of what you've done before, right? And it predicts what is more likely to have happened. So the cat chased is very highly probable. The cat sang and the cat smiled, right? So how does it find out that these are the words that it should? It can only give you 3-4 options, right? So how does it know which are the most? You obviously want options that are useful so that you don't have to type. You can keep choosing the next word, right? And that in the previous cases was done by something by looking at the probabilities, the probability of the word cat given the word the, right? Or the probability of the word chased given the word the and cat. These are called bigram, trigram models. Okay, they are going to only look at the counts, right? So probability of the cat given the is nothing but the probability of the and cat occurring simultaneously, joint probability divided by the probability of the, that can be given by a count version of frequencies, I mean probabilities, right? And I can do this, right? So there are many methods to do this. So there are many toolkits, SRI toolkit, IRSTLM toolkit, even there's something called KenLM, right? Ken language model toolkit, which is also basically an n-gram model, right? And why do we worry about this? Because the language model, acoustic models generally help you about 65-70%. The remaining 30% performance gets by the language model, right? So recognized speech is much more rarer. So it's most probably that the person said recognize speech. Okay, so this is the beauty of this thing. And now I'm going to say that this is very naive, very old-fashioned approach, right? It cannot keep track of past very easily, right? If I have to look at 5 words in the past, I have to need a 6 gram, and that is going to be very difficult to find this joint probabilities. Okay, so that's where this concept of a recurrent neural network language model came. It comes from Mikolov. We actually collaborate with his advisor Honza a lot. Okay, these guys are from Czech Republic, right? And so the idea of recurrent neural networks is given start of a sentence, I predict the probability of the next word. Let's say it's the, high probability, then the given cat, and then cat given chased. Okay, but now I also want to have it's not only individual guys like this. I also want the history, right? So if I give the history the cat, then probably chased is going to be highly probable, right? So having knowledge about the previous inputs is going to make my output much more better. And that's the whole idea of an RNN language model. It's similar to a bigram or trigram, okay, but it looks a lot in the history, right? So for example, if I say I grew up in Assam where I went to school also, and therefore I speak fluent, if I had all these words, right, you know that which word determines what I'm going to say next. It is this keyword, right? Assam, right? And if I had that history, then I would have been able to predict Assamese very easily. But in a bigram or trigram, I would have had a history only till here, right? 4 gram, 5 gram. I'll have only history till here. With these previous words, there's no way I could have anticipated. That it is Assamese, right? So recurrent neural networks can keep track of a long history. Okay. Professor Prasanna, can I get another 15 minutes? I have still
perfectly fine, sir. Perfectly fine.
I'm really sorry keeping you guys away from lunch. But
we have one more session, sir.
Oh, okay.
No problem.
Okay, sorry. Just since I've come this far, I just want to finish it. Okay, yeah. So the whole idea of recurrent neural networks is one big application is language modeling, right? And now we'll see something called transformer LM, right? The beauty is that it can look further into the history than compared to a bigram or a trigram model. Okay, now comes the question, right? If I want to use words, right, how your keyboard in your mobile phone, how is it predicting the next words? Remember, I'm talking about neural networks. These operate on numbers, right? Some features, which are a collection of numbers. But here I'm talking about words, right? So I have to know how to represent words in terms of vectors, right? And the simplest thing that I can do is, let's say I have 10,000 words in my vocabulary, right? So the first word, I'll put 1 in the first place. I'll have a 10,000 dimensional vector and put zeros everywhere else. Then cat, right? So that's my second word. Then I'll put 0 everywhere except in the second place, 1. Chase, third place. And like that, I can go for 10,000 words. So each one of them will be a 10,000 dimensional vector, but only each word will have only one non-zero entry. All the others will be 0. This is called a one hot vector, right? So instead of my neural networks can handle only vectors of numbers, therefore I replace the with this 10,000 dimensional vector here. I replace cat with this 10,000 dimensional vector here. And remember, for my supervision also, I need a 10,000 dimensional target vector here, right? And therefore, I have to find out between the output of this and the 10,000 vector, what is the loss, and then back propagate, right? This seems like a waste of vectors, right? Because each vector has only one non-zero entry. It's so sparse. All the others are zero, right? Therefore, this guy Mikolov came up with this idea. Let me look at context and try to predict the guys. See, if I'm looking at cat, let me look at what word occurred before and what word occurred afterwards, and try to get a vector for cat. Okay. So this is the idea of word to vec. Again, this comes from Mikolov, right? So so suppose the cute cat, then there are some blanks here. The cute cat jumped over the lazy dog, right? So I can have one hot vector, 10,000 dimensional vector the 10,000 dimensional vector cute, and I'll try to predict the word cat, which is also one 10,000 dimensional vector, based on these two previous words and the next two words, let's say jumped and over. So this has two words to the left and two words to the right as context, right? And then I have a matrix that will reduce the dimensionality to, let's say, 500. And from this 500 dimensional vector, I have another matrix that generates back a 10,000 dimensional vector. Is this clear to everyone? So I am trying to get, predict cat, right? Because cute cat, I'm going to predict the cute jumps over by looking at one dimensional 10,000 dimensional vector here, 10,000 dimensional vector here again 10,000, 10,000, and predict another 10,000 dimensional vector at the output, but by going through two matrices, one which will reduce the dimension to 500 and another that again increases the dimension to 10,000. Here I will get some error, right? Softmax will happen, right? Again here softmax, that's where, because I might have 10,000 words, the denominator has to be compensated by noise contrastive estimation, right? Otherwise, it's very cumbersome, right? So this idea of contrastive predictive coding and all borrows from here, right? And basically, we do this. If any of you know some pattern recognition, all that I'm doing is, if I look at this, it's doing some matrix multiplication and reducing the dimension to 500. So what is this process? Where do we do this dimensionality reduction? What is this process called? Can someone tell me or put on the chat box? When I have a big vector and I do something to reduce the dimension to a smaller space, what is that operation called in pattern, or when you're talking features in many things, right? Encoding, so we have this idea of what's called principal component analysis, right? It points to directions where most of the energy is preserved, right? So that is basically the idea here. This is a PCA, right? This is a glorified PCA. This is just principal component analysis, right? Which reduces your dimension to 500. Okay. And the terms that we use are called embeddings, right? So this is basically statistical method. Okay. But there is the nonlinearity is only there are no nonlinearities here. Okay. There's a matrix. There's a matrix. So it is a PCA, except for, of course, I'm using a softmax here. Okay. And these are called embeddings, right? So, and there are many, Glove is another thing from Stanford and so many other things, right? So this is now a 500 dimensional vector, which is dense. It has all non-zero values, okay? So, but I do this for the entire vocabulary. I take 10,000 words. I mean, I take all the text from all over the world, like Wikipedia pages, newspapers, everything, and take unique words, right? And the unique words might be only 10,000, and I find out this for all of the sentences that I've borrowed. I finally find a matrix, right? So given any word, I multiply with this matrix and get its embedding, right? So now this is a fixed embedding. Why is it a fixed embedding? For every word I have the one hot vector, I multiply with the matrix is fixed for the entire, I've trained the word to vec representation. That's it, only one time job. This matrix gets fixed, and for every time the comes, always it's going to be only one embedding. So there is only one unique embedding for the word the, one unique embedding for the word cute. Okay, so this is called fixed representation, right? And the amazing thing is when you look in this smaller dimensional space, it's beautiful in the sense that king and man are very close vectorially, distance wise. Queen and women are very close, right? In France and Paris, England and London, Italy and Rome are very close. So you can easily see the relationships. It's saying country and its capital, country and its capital, country and its capital. So these kind of embeddings capture very powerful representations where vectors that are close to each other have very strong connection semantically, meaning wise. There is some strong connections. Okay, so this is the basic idea of word to vec. Okay, and now I come to what's called the encoder decoder models. Okay, and this happened around 2015. So till now, if you remember, I took how are you, right? It's basically, the you is basically using knowledge of are and how. So what happened in the history, and it's helping me predict better what the next word or character should be. Okay, but if I'm looking at translation, for example, right, the translation now is going to be dependent on the whole sentence, right? So I'm going to use this whole sentence, and I don't individually translate how are you, right? That will not make sense. How is what? Kaise? I'm not very good in Hindi. You is aap, right? So kaise aap something, that's not going to work out. So what we do is, this is Badunu's idea, right? And Badunu's, this is an MS, I think, summer internship kind of a work, okay, with Bengio. Okay, so you can see that even summer internships can lead to some amazing, improvements, right? So this whole idea is, I captured this entire history by this context vector, the last context vector, and feed it. And now what I'm going to do is I'm going to do translation task. Okay, before previously they used to do translation task using statistical methods, but this is one of the methods that really used encoder decoder recurrent neural network framework. Right now, what should be the next input here? Here, these are the words in English that I know, but given these words, I have to anticipate what should be the output, right? And therefore, while training, I might know what the output is, but while decoding, while testing, I will not know. So there should be some input. And so every step here, you see, there is a previous input coming and a new input coming. So what we do here is we use this previous output to feed here, right? And then given this output and up, it produces kaise and then hai. Okay. So basically, all of this is captured by a context-dependent vector. And then I use this vector to predict what was the output, translated output, right? Aap kaise hain, right? So you can see two things have happened. There's two RNNs, but these are now modeled by using LSTM cells, right? Because to avoid the exploding gradient and vanishing gradient. But there is now this concept of what's called an encoder and a decoder, right? So the encoder takes and collapses all this information, or captures or condenses all this information into one vector and feeds it, and it gives the output, right? So this is the first encoder decoder structure that came, and this is also called a sequence to sequence model, because I take a sequence of words and produce a sequence of words in another language, right? So a sequence of Hindi words, right? So this was one of the great jumps in translation, right? And now you'll start seeing that we keep borrowing from each other, right? If it is a sequence of vectors, in this case words, I get a sequence of outputs here. Who stops me from saying, why can't I use a sequence of acoustic vectors and give me an output here? Of course, in this case, I won't be doing translation. I'll be doing the Hindi speech signal. I'll take the sequence of acoustic MEL filter bank vectors and capture this and output the characters of words. I put words here, but you can use characters, right? Using CTC or something, right? So I can do something fancy here, correct? So in fact, this is not CTC. It is going to be a language model kind of thing. So it's a decoder structure. It'll be capturing the outputs in terms of characters, right? So if I can do sequence to sequence for vectors, I can do for question answering, right? So I can say I have a sequence of words which is a question, and I can have a sequence of like a chat bot or something. I can have a sequence of outputs. So in all of this, what am I doing? I have to train this network, right? Which means I need a lot of parallel data. So if I have the English sentence here, I need to find out the Hindi sentence here, right? So somebody has to manually translate and tell me what is the output, right? And I have to do it for a million sentences before I can get decent accuracy, right? So similarly, when I'm doing speech recognition, I give the waveform. I know what the output should be. This is a Hindi speech recognition. And so somebody has to listen to the audio and give me the Hindi text output, right? So this is called transcription, right? Manually, somebody has to transcribe. Somebody has to manually translate before I can train the system, right? Or somebody has to give me question and answers before I can build a good question answering system, right? But the concept of speech to speech or sequence to sequence is coming through, okay? And there have been many improvements. Why feed only one vector? Why not feed this vector to every input? Then why not take all the outputs, the embeddings, what we call, and feed it through this, right? Here it's still a constant, or for every input I can change it. And this is basically where we get finally to this concept of attention, right? So given at every step, I attend to all of these vectors, look at it, and then give one input. Again, for the next step, I take all of this guy, and output something here. Okay, so these are called attention-based encoder decoder. So there is an encoder, there's a decoder. That's why this term comes. And attention means to get this context vector. I'm not only going to take this input, I'm going to take every input here to get one output here, right? So it's attending to all these vectors, right? And therefore, this is called attention-based encoder decoder. This is how Google, Microsoft, and many of these guys use. So they do use transformers, but many of their commercial stable systems still use attention-based encoder decoder. Okay, so that is one concept, right? And now comes this idea of transformer, which changed the world in the way we do. Which again is a sequence to sequence model. It again uses attention. It again uses encoder. It again uses decoder, right? But the components within the encoder and the decoder, there are many such encoder layers. There are many such decoder layers. So this transformer also came from a machine translation perspective. But let me just point out what are the problems in a recurrent neural network. One is if I'm going, you could have forward and backward recurrent, right? The bi-LSTM, right? But basically, if I'm looking at this guy, right, its connection to the, if it's 10 words behind, is very, very, it reduces in the sense it has to go through many hoops, right? So the effect of X1 on XM is not that dominant as XM on XM minus 1. Okay, that's one aspect that's important, right? And so distances matter. So it does not treat equally important. This guy is not equally influenced by XM minus 1 and X1. In fact, X1 will have lesser influence than XM minus 1. Okay, so this is a problem in recurrent neural networks, right? And bidirectional, I'll go only one direction or the other direction. But in any case, X1 and XM, even if I go in the left direction, are very far apart, right? So that's one aspect. I skipped one history, which is called convolutional sequence to sequence. The other problem is it's sequential. After I compute this step only, I can come here and compute the step. After this only, I can compute and come here. So only after this is completed can I come here, then I can come here, then only I can go here. So in terms of implementation, it's going to be very slow because it's going through sequentially. Okay, and so convolutional sequence to sequence, try to avoid that by parallelizing. And transformers basically exploit it. So transformers basically do two things, right? At any given feature vector, it takes a linear combination of all the other feature vectors. So VT depends on V1, V2, V3, V capital T. Similarly, V capital T will depend on VT small t, V small t minus 1, V2, V1. So each one of these guys will depend on all of the representations, inputs, okay? And therefore, this is called self-attention. It equally attends to all of the frames, okay, or all of the words, and the importance or the attention is come through the beta, okay? So the distance does not matter, and the direction also does not matter, okay? So and it can be parallelized because each one depends on every one of them. I can parallelly move along the path, okay? So many advantages with self-attention and transformer. I can instead of sequential, I can do parallel. I need not do this, I can pay equal attention to all of the feature vectors. There's one problem with self-attention, which is if I replace V1 or interchange V1 with VT, right? this guy is not going to get changed at all, right? Because it's just taking parallelly all of these guys. So if V1 and Vt are interchanged, the answer will not change. And that's because we are not capturing the sequential information that V1 occurred first, then V2, then Vt. That is not present in the self-attention part of it. And therefore, we give additional information through something called positional encoding. Okay, so that helps. So we are going to say this is in the first position, V2 is in the second position, Vt is in the small tth position, V capital T is in the capital T, and that's how the sequence information is preserved. Okay, so now the transformers have solved many of the problems. They can parallelize, right? And they can do fast because of parallelization. The distance is not a problem, and therefore the transformers made another big jump in machine translation. So how are you now? It takes all of these inputs, and then through the each one of them has self-attention, and then they have something called source attention, and then again these guys have self-attention, and you get back fully trained network. Okay, so here the training part is parallelizable, right? But and you can see this is from JLMR. You can see he's got very wonderful tutorials, right? So let me it went off too fast for me. I'll show you everything is parallel. Okay, nothing is sequential. Just give me a minute. Yeah, now you see here it'll go parallelly. So that parallel operation you can do quickly, and so you know however long it it's all parallel. It comes in one shot and then comes here and then it goes. This part is of course sequential. Okay, so we'll come to that later. So now this is decoding part. So it is going to be sequential information. We see that this is essentially similar to what we will do in a language model. So we'll come to it. This is how now transformer language models are built and GPT are built. I'll come to the right part of it here. Okay, so here it is still sequential in nature, but while training, I know what the input and output. They're just right shifted by one word, right? And therefore I can parallelize the training part. Okay, so transformers made a big change, right? And if again we know that if this is a sequence of words, I can replace that with a sequence of acoustic vectors. So transformers, we are one of the first guys who moved to transformers in speech recognition. So transformers now have a sequence of acoustic vectors with positional encoding and a set of encoder layers, and then a set of decoder layers, and interrelated through this what's called source attention. And then we output characters or what's called byte pair encodings, right? So this is essentially something we started doing in 2018, kind of 19 kind of thing, right? And this is transformers work very well, right? And of course, they still need this, what's called supervision, right? These are my acoustic vectors. I have to know what are the corresponding characters, okay? But the beauty is in this kind of thing, I don't need a dictionary. In a transformer, as I told you, there's indirectly the language model coming into picture. So transformers can be robust. They don't need a language model as much as, let's say, a CTC based method. A CTC based method necessarily needs a very strong language model. For example, your phase-seek based methods, because of legacy issues, they only stick with CTC. For them, language models are very important. And they even stick with basically characters. They don't even go to BPs. Okay, was there any question? Yeah.
Swapnil has raised a hand.
Huh?
Yes, sir. Yes, sir. Transformer can be used for handwritten recognition also. The concept, right?
It's a sequence to sequence, right? So you can do sequence of anything to sequence of anything. You can use transformers.
Okay, thank you, sir.
Yeah, definitely.
Sir, but these transformer models might be very large, right?
Yeah. All of these are data driven. So large in the sense, I'm missing the point.
So after we train the model and everything is done, then we have to deploy it somewhere. So at that stage, the model will be very large.
Yes.
Which can be an issue, right?
I mean, it depends on your compute power and so on. If you're doing you can do something called distillation. You can reduce the framework and all that, right? So you can have a very powerful teacher and then distill it to a smaller network. Okay, I definitely if it's on the cloud, it's very, very trivial, right? If it's on the edge, the transformers work very well, but the problem is if you look at codes like ESPNet and all that. The issue is more about the way the decoders are implemented. That is why it is slow. Okay, it is not. I mean, I'm sure you can do it almost. With today's mobile, I'm sure if you distill it, you should be able to do it. But the decoders are still, if you look at any standard framework of ESP.NET, they're decoders. So if you write a good decoder, I think it should not. Nowadays, they use for streaming services, right? So if you distill it, you can reduce the parameter count significantly. Okay, but definitely, if you have a cloud, nothing like that. Does that answer your question?
Yes, sir.
Okay, so if you do on the cloud, you're all set. Okay, but if you're trying to do on the edge, then you have to be a little more careful. Yeah. And I agree with you, and I keep telling people, this transformer does not solve all your things, and it should not be used everywhere. For example, if I'm doing only digit recognition, or farmer, mandi and all, our GMM, HMM system, or call these TDNN, right, will work wonderfully well. Okay, it will be better than these guys, because if you don't have enough data, you're not going to train a very good network here, right? So therefore, you have to know what engine to use where. So for example, if you have a bus engine, you don't want to put it on your moped, no? So you should know what your application is and what you want to do with it. Obviously, in a moped, you don't expect speed to be at 90 kilometers per hour, right? So there is all these issues have to be worked out. So there is going to be some compromise somewhere, but the vocabulary, if it's limited, with a small thing, I can do, fast deployment, less memory space, less power consumption, right? So a lot of this, if the computer is less, the battery power is also going to be less for mobile devices, right? So there are implementation, as I said, engineering is a large part of deployment. So we can build the best system, but whether it's useful for a particular application will depend on the application, right? So that's a very good question, and I keep telling, as engineers, we should know what to use for what. Don't use a machine gun to kill mosquitoes. Okay, so let me go through some. We have lots of demos, right? We built some things for so we have NPTEL lectures. I don't know, many of you might have heard of it. So these are unfortunately in English. So one of the big issues, what we are planning in the mission is to actually have it automatically translated into multiple languages, right? People prefer to learn. They might have come from Hindi medium school or Tamil medium school or Telugu medium school, right? Especially first year engineering, right? It's a big, and I have experienced in my own class, we have to put TAs who know Hindi to help students. It's just language is a barrier, right? And unfortunately, English is something that's common, so we have to use it. So whether we can do translation to other things. So here the first step is, of course, somebody has to manually sit and type what the professor said. So that's called ASR, right? Transcription. So we built a transcription based on this ASR transformer model, right? So you can see that we do much better than this is some evaluation done by CDAC, right? And this is obviously expected because we are making it for a specific task, in this case technical lectures, right? And Google obviously is built for general purpose, right? It's not meant for this kind of task. And you can see Amazon or Microsoft, we are much, this is word error rate. The smaller, the better, right? How many errors it's making. So it's making about 15 errors per 100 words. This is making every 2 words is an error. This every 4 words is an error, right? So many agencies have tested. So and in fact, there are not only Google's, there are many transcription agencies in the world, right? Temi, Transcribe. I think Temi, Otter, if I'm not mistaken, is the one that's now combining with Zoom to provide your captioning. Okay, so Otter is a very good company, right? Again, see, Otter is based on some 4 or 5 Chinese guys who have sat and done, I think Temi or Otter, one of them. So but we are competitive, right? So we are about 5.5. Many of them are plus 10 plus kind of thing, and they're all cost things, right? So the bottom line in all of this is, it's with enough, with 2 weeks you can build, but don't get arrogant. Okay, in 2 weeks you should get excited and say that I can change the world, right? And I want you to change the world. I want at least 10 of you to build. Why should there be only this? We should have Indian version of all of these guys in Indian languages, right? And make money, right? Obviously, if you can provide employment, you can employ other guys, right? So if you make money, you can employ many more, and we can build a big AI community, right? So it's important that we do that. And just to sort of take the last topic, which is the hottest now in the last 6 months to a year, is this idea of supervision. Remember, till now, everywhere I have used supervision, right? So I gave some input here. I know what was expected output, and then I trained the network. Okay, so so here what we are looking at is something slightly different, right? So it's very expensive. Can I get away without doing this, without this supervision, right? So here, if I give translation, I know what is the English text, and I know what is the Hindi text. If I'm doing ASR, I know what is the in English audio input and the corresponding text output, right? But can I learn something more only by using one of the data pieces? If I have only audio, can I do something? If I have only text, can I do something, right? For example, language modeling is a self-supervised, unsupervised kind of training, right? So basically, I'm only using text to learn, predict the next text, right? So I'm not using any supervision. So that is a self-supervised kind of a framework, right? So this is a self-supervised framework, right? So from this text only, I learned the embeddings, right? So the whole idea got inspired by this, right? So if I can use some context to learn embeddings, in this case, word to vec, the whole vocabulary was captured in this one matrix, which reduced the dimension to small, right? So this is one matrix. Should I not be looking at different versions of this vector for the itself, depending on whether the occurred after queued, before queued, the occurred after India, so on, right? So the context, so this is one fixed representation. So the idea of context-based representations came. It's inspired by BERT, right? It's inspired by transformers. And what essential idea in something called BERT is to get this context. So here, if I had the one hot vector, I would have done word embedding and got this 500-dimensional vector. But that 500-dimensional vector is same for dog, irrespective of what context it occurred, right? So now, BERT is basically the idea that depending on my left and right context, can this vector be changed, right? So dog will have a different word embedding depending on whether it was my dog is queued or the dog jumped. Every one of them, you will get a slightly different representation. And here it's like, I don't need any supervision by, manually training anything, manually doing anything. All that I'm going to do is mask this. What do you mean mask? We'll put a vector, specific vector here, and try to get back the dog vector here, the dog embedding, this embedding. Now, first I moved from one hot vector to embedding. Now I'm moving from one, word embedding to contextual embedding here. So here it will be the word embedding, and here I'll get a contextual embedding. The word contextual is important. Depending on the context in which the dog occurs, this embedding is going to change. So dog itself will have many representations. So this is much more richer representation. So why are we doing this? Remember, we are trying to feed vectors to neural network. Originally, for every word, there's only one kind of vector that came. Now, for every word, depending on the context, I'll get a much more richer representation. So these are just representation for words, right? These are like features for words. So we are learning a richer feature or a richer representation, okay? And this is the basic idea of BERT, right? So I went from fixed embeddings in word to vec to contextual embeddings, and BERT also addresses this next sentence prediction and so on. But the basic idea in BERT is contextual embeddings, right? A richer representation, okay? And of course, downstream tasks, they will tell you will do better. I'm not getting into it. Then comes this part of the BERT uses something called the encoder part, right? In a transformer. So remember, transformer has two parts, the encoder and the decoder, right? So the BERT uses only word embeddings here, which are coming from word to vec, and it's getting contextual embeddings here. And of course, next sentence prediction also it can do. It does not use the decoder part. Okay. Now GPT uses the opposite. It uses only the decoder. But remember, the decoder I have to feed the next input, so it is going to be sequential. So decoders are going to be sequential in nature, but while training, I can parallelize it. So that gives rise to, so BERT is this. GPT is basically taking the decoder and feeding one after the other, right? So this is basically a language model, right? So I can predict the next word given the history of these things, right? So this is essentially what the purpose of a language model is. And we know GPT can even write books today, right? So that is basically the idea of GPT, right? And now I'm going to finish off by talking something called contrastive predictive coding. And this is basically inspiring our new representation learning, so like wave to vec, right? Which basically started with Jim Glass and Chung from MIT. They tried, for speech to predict the here, I'm trying to predict, depending on the context, a different vector, right? So similarly, here they're trying to predict if you look at GPT, based on the history, I'm trying to predict the next word, right? So this is like a language modeling, right? So similarly, if I give x1 vector, can I predict the 1 plus nth vector, x2 vector, 2 plus nth vector? So I'm learning a network. This is again self-supervised because I'm using the same input shifted by n time frames, right? So again, it's self-supervised, very similar to our GPT method. And so if this is happening, why not use Mockingjay, right? So that's basically, oh, what happened to Mockingjay? So there is Mockingjay is very close to the concept of BERT, right? So if I mask some of these guys, can I get back the representation for that particular speech sound? And that's what Mockingjay and SpeechBird. Actually, we worked a lot on this, but somehow we could never make it work. Or we didn't get that much improvement, but we were using 100 hours data. But I think if we had used LibriSpeech or something, we would have done better, right? So this is BERT inspired. This is inspired by GPT or contextual embeddings, right? And then the contrastive part, remember I told you that in wave to vec and all, the denominator we do negative sampling. So that concept is borrowed here. And so we do the whole idea of wave to vec is actually, the credit should go to Vanden Wood. Okay, he's the guy who came up with contrastive predictive coding and contrastive losses and predictive coding, and that what led to wave to vec 1. Okay, I am going to skip because I think I've gone way too much behind. Then they quantized it, that became wave to vec quantized, and basically all of these are representation learnings. So wave to vec 2.0 is basically again quantized. Again, you have contextual contrastive predictive losses, right? Which is somewhat like a denominator is going to have negative samples, right? And then finally you have Hubert, which basically is coming back to our SpeechBird, which basically tries to mask from and try to quantize it by using k-means or any of the other methods, right? So here there's no contrastive losses. Okay, so and each one of them gives you some benefit. So Hubert is now the state of the art, right? Again, there are many problems with self-supervision. You have to worry about context, right, and domains, and so many other things. Okay, and just to show off a little bit of what we have done, can I just share with you our some samples, right? Which I'll just give you some for NPTEL. I'll just see if I can share some videos or something and. So this is some NPTEL video. Okay, so you can upload it. It'll take some time. Okay, so I don't know how big this video is. So I don't know. Sorry, Prasanna, but I thought
perfectly fine, perfectly fine. Please. So next speaker we will have from 1 to 2 p.m.
Sorry,
no problem.
I just play out. So
those are available are in different forms. Like data can be in the form of integers,
you can mute your mic, sir.
floating point values. It can be formed in the form of a character or string, and there are many other complex type of data, the table, graph, or whatever it is there. And what exactly the need is that a method should be in such a way that whatever be the data, you don't have to bother about. In other words, so far the concept.
Please unmute, sir. Unmute your mic. Sorry.
So we can do, you can see that it recognizes well. In fact, the same model, right? We have done it even for general English. Okay, it's called general English, but it uses the same model. Obviously, you can see that the domains are different. Okay, but it'll do something, but it'll still make mistakes, but it's not so bad. For example, I can, you know, I can even, I don't know which is English in this. Is this English? I don't know. It's Hindi. It says 1 minute. So,
Pata Sridhar has a question, sir. How did you get punctuation here?
So okay. I'll show you one thing that I found very interesting. Let me go back to my slide. Okay. Let me go back to the slide and play one of these things. This is again automatic. I'll just play this video. Okay. And you can see the denominator. Okay.
But what is available outside is only that fraction which is falling such that my theta I is less than theta c. Okay, theta I is greater than theta c would imply total internal reflection.
So the idea is that, so when you land here, okay, now if you land, if you're lucky, and then, you know, for example, if these are all integer coordinates, you would of course land somewhere, you know, on this grid where you have integer locations. But suppose, let's say your tx is something like 3.7 and ty is something else, let's say minus 1.5 or something, then it means that you will land in some area which is normal.
Is, yeah, how do we get it? So these are all trained with it. Since my data has a lot of this theta, alpha, and all that, right? It'll pick up the characters as it is. So you can see theta I, theta c comes nicely. Normally, you know, when they normalize, it'll be THETA, and that's even more difficult to read, right? So all of this is because the trained data is done in such a way. Okay, so that's the beauty of all of these deep learning methods. So whatever data you give, right, if it's rich, it'll also capture that richness in transcription, in punctuation, in symbols, right? That's the beauty of all of this. So if we can do wonderful things, that's what I'm saying. So you know, deep learning, you know, machine learning, all these things, networks give you the power, but be modest. Okay, so you're only starting, so don't expect miracles. Yeah. Any other questions? So this is what I wanted to show. We have for Hindi also. In fact, for Hindi also, my student is very proud. I don't know. I'll show you one Hindi thing and stop there. Okay, so this is not that great because we have only 190 hours or something. But I don't know. Ravi Shankar Prasad speaks Hindi. Yeah? Okay. So let me just, I don't know, this looks like Hindi news. Okay, let me upload this. So many of you may know Hindi. Okay, it's not perfect, but we don't have much data. The question is, the more data you have, the better your systems are going to be. So these are all data-driven systems, right? In Hindi, I think we took a lot from news broadcasts. So we have, again, I want to say that we have released some data. Please, we want to release more data. We are just struggling, you know, catching up and cleaning it up. But if you have any feedback, or if you are able to do some good things with the data, please share with us. You know, we'd be happy with whatever, we can help you with, right? And of course, Professor Prasanna, and I see Samudra Vijay sir is there, so he's a wonderful person, right? So
sir, you can mute and play, sir.
I did wrong. I didn't go to Hindi at all, sorry.
Oh, this is some other English, this one, sir.
Yeah, so yeah, I used English ASR for it, sorry.
Yes, sir.
What is Professor Samudra Vijay giving? Next is 1 to 2. What is the lecture on?
Sir, 1 to 2, Vivek Raghavan will give on this, their efforts for this data collection strategies and those things.
Okay. Yeah, so it has to be a collective effort, right? So they have collected a lot of data. They have done some wonderful things. So
yes.
And so let's hope everybody. I'm just waiting for it to.
That they are also made it available, sir, in the public domain.
Yeah.
But, effort and
is this Hindi?
Hindi, yes.
It is Hindi, yeah? Okay. Mute it. Okay. And
you can mute your mic and then play, sir.
समय भी वो चुनाव प्रचार के लिए बाहर गए हुए हैं, लेकिन अभी थोड़ी देर में यहाँ आने वाले हैं और हम यहाँ उनका इंतजार कर रहे हैं एक बहुत ही स्पेशल इंटरव्यू के लिए। आपने प्रधानमंत्री मोदी के अब तक बहुत सारे इंटरव्यूज देख लिए होंगे। आपने उनका बाग बगीचे वाला इंटरव्यू देखा होगा, आपने उनका बनारस के घाट पर इंटरव्यू देखा होगा, आपने उनका स्टेडियम में इंटरव्यू देखा होगा, आपने उनका गैर राजनीतिक इंटरव्यू भी देखा होगा। लेकिन आज का जो इंटरव्यू हम करने वाले हैं ये उनका शुद्ध राजनीतिक इंटरव्यू होगा। इसमें आप बैकग्राउंड पर मत जाइएगा, इसमें आप बैक टू बेसिक्स यानी बेसिक्स पर जाइएगा। इस बार हम बैकग्राउंड पर ध्यान नहीं देंगे, इस बार हम बेसिक्स पर ध्यान देंगे, यानी जो मूल मुद्दे हैं, जो मूल सवाल हैं वो हम उनसे आज पूछने वाले हैं। और मूल सवाल क्या है, जब भी आप बाहर निकलते हैं, हम भी जब बाहर जाते हैं तो पूरा देश एक ही सवाल पूछ रहा है कि चुनाव के बाद।
Please unmute, sir. Unmute your mic.
Yeah, so it does make Banaras became Banaraha or something degree, but you can see almost if you look at word error rates, will be sub 10%, right?
Correct.
But the question is, it all depends on the domain. So luckily this was news domain, so it works well, right? So I am, I've taken a lot of your time, but I hope it was, somewhat, at least, some overviews there. Any questions, I'd be happy to answer.
Yeah, any questions from any of the participants? Please unmute your mic or type the question.
There is a question over there in the chat box.
Oh, so, I'm trying to build an ASR model in Arunachal. Don't have much data. Okay, so data is the king. With very little data, right? We have to go to a little, so it's evolution. So if you look at the conventional GMM, HMM kind of thing, they need less data, but a transcribed kind of data, right? And the other end is where we have a lot of, supervised kind of unsupervised, self-supervised kind of models, which can be kind of fine-tuned to this, right? So I hope, both of these will be covered in this workshop. I think initially they start with the simple model, and at the other extreme is where I can use a lot of other data, which is called transfer learning, basically, right? So to build for a particular language, it's difficult to answer specifically because it depends on how close the pre-trained models are to your particular language and task and so on, right? So I know there's no clean answer to it, but yes. I would suspect.
Hello, sir.
Yeah.
Hello, sir. Actually, this was my question. Actually, I am working on a Arunachal tribal language. So this language don't have such kind of data set or some videos or any news. Nothing is available actually. So low resource, very low resource, endangered language according to UNESCO. So for work such kind of language, so we have to collect data, then we have to make the transcription, and then we can use in a particular model. So it will take time. So as I am a PhD scholar, I have to complete my work within a certain time as per the institute norms. So what is your suggestion that which type of model like Kaldi or any type of toolkit, what should I use? Because the deep learning network needs lots of data as per your lecture.
Correct. So see, Kaldi, there are infinite toolkits, but most popular, of course, Kaldi and ESPNet and FairSeek, right? These are three popular toolkits, but they all provide similar kind of flexibility to you, right? But what I would suggest in your case is you will have to depend on somebody, some of us, right? In the sense, we have to have some pre-trained models. So you can have a transformer-based multilingual model, right? We have done some work where we do, what's called common label set kind of a framework, right? So where we can do zero resource or low resource languages. But as of now, even we don't have that kind of full data to give you decent performance for Arunachal Pradesh, right? So Arunachal tribal languages. So one possibility is, I think, the wave to wake kind of thing. But again, my worry is that domain and language dependence will come hugely into play, right? Arunachal is, I assume, some kind of Indo-Aryan, I don't know. Will Prasanna, somebody know? Is it part of that category or?
I also don't know, sir.
Some of them are Tibeto-Burman, many of them.
Oh, Tibeto-Burman. Okay. See, yeah, but I mean, if there's enough data and your domain is very, very small, specific domain, I think very few words or limited vocabulary kind of thing, you should be able to get away with any of these methods, whether it's wave to wake or transformer based common label set that we use. Okay. So you'll have to contact us separately and we'll see how to help. You go through this workshop. At the end of the workshop, maybe you'll have a better picture and you can answer this question.
Yes. So I wanted to say the same thing to Sajal sir. Once he completes this workshop, I think he will be in a better position to decide, and also we will help you out. That's not an issue.
Thank you, sir. Thank you very much.
Any other questions from any of the participants? Jeevan Revanappa, he has asked a question.
Well, see, this is where see the acoustic parts. Definitely, there'll be hit in performance. Okay, the question is how much you can transfer. So the acoustics. In many of the models, we are going to also be influenced by indirectly with what's called the internal language model. For transformers, for example, or your wave to wake, there is an implicit learning of context that comes into picture, right? So definitely, when you take a pre-trained English and use Hindi, there's definitely going to be a big hit. Okay, so but if you can put some amount of Hindi data into it, it'll learn. Okay, but cross-lingual, it's going to take a big hit.
Yeah, definitely. Any other questions? Sir, otherwise, sir, okay, thank you. Oh, okay. Sir, thank you very much for kindly agreeing the invitation and also spending completely today.
Yes, but I had to cover quite a bit, but I'm happy. I mean, you people are putting so much effort. The least we can do is at least talk a little bit, right? So
thank you very much, sir.
Thanks again for inviting me, and thanks for all the efforts, right from IIT, IIT Dharwad, Step, and everybody. Yeah.
Yes, sir. Yes.
Thank you, sir. Thank you so much.
Thank you. Yeah.
We will share the presentation.
Yeah, the video will be there. Yeah,
the video will be there. We can use that, Ajay. So we will have a small break at 1 p.m. sharp. We'll start the next talk, 1 to 2 p.m. because the speaker is having other meetings after 2 p.m. So let us meet at 1 p.m. and listen to Vivek Raghavan. Thank you very much, sir.
Thank you.
Thank you.
Bye.
Bye, sir. Bye, sir.